To the audience, you can also tell your colleagues to look at the YouTube. Everything will be live streamed. USB.
USB na lang. Or laptop.
Ito lang. Ano yan? Tagal yun na siya ng
1 minute.
33. 1 minute lang. Kundi lang.
Nakita na yun.
Bukan sabihin niyo sir, pag start na, 8:20 na.
Si Richard.
Nandito, ayun o. Sama ni ano. Ibang Richard.
Ano? Hindi mo nabibigay sa akin.
Ano gagawin?
Sa PowerPoint. Okay.
PowerPoint na.
Pinapaprint ng check. Lahat. Yung lahat.
Pinapaprint?
O yung sa AIRSCAN.
Atin na lang.
Oo. Ako ba ka? Sabihin ko sa'yo. Akit ako. Thank you.
Print out. Yung PSU.
Sige na, malang Japon. Pula Paul, ay 15. Avanse. Tirahan na court. Na-shot. Grabe. 1-4-10 around na replay. 1-4-10 1-4-10 of course. Bang. Daog pa. Why? Number 9. Number 10 ng 1. Number 2 ng gusto. Kaya galagas na ang mornets mo. Kaya number 8 ang miyame. Sige daw, pwede mo ito namin yung miyame. Yan eh. Para sa aling anis naman, ito lang.
Yes, I was just telling everyone that we are also being streamed at other locations. UPA Las Bañas, Anderson State University, and Central Luzon State, offline. Central Luzon State University. So we can probably start. But I'll give a brief overview of. Hello. Okay, maybe this one's good. So welcome everyone. This is one of the two-part workshop seminar that we have this afternoon. This morning, this is about drone technologies for large urban environments. In the afternoon, there will be research opportunities on electric grids. So this is a morning and afternoon workshop. Before we start, I guess we have audience from Samsung, grad students, genetic engineering from UAS, Sir Montalibano, graduate students, BGE, Department of Genetic Engineering. Ariel Blanco is here, the former chair of BGE. So we'll start with the national anthem. Jing. Kindly everyone stand. Very much. UP Baguio is now online. So, to give us opening remarks. The director of the Electrical Electronics Engineering Institute, Dr. Richard Dizon, is here, our director.
Hi. So, good morning, everyone. I'd like to welcome you here at the Institute on this very momentous occasion that we are able to share our knowledge with you together with our esteemed partners from Berkeley, Claire and Alan, who will be with us this morning. So I look forward to a very nice interaction between everyone. So I'd like to put some historical background to Picari in a way. So back in early 2000, we had this initiative with UC Berkeley back then, wherein we were getting tapes for master's and graduate courses for IC design related courses. It was through CalView. I still remember having to watch these videos because the online facilities weren't really set up way back then in the Philippines. So we would get our course administrator from the US. And I remember having to take at least 6 to 7 courses from UC Berkeley. And going back now, using that perspective to what we have right now, things are much more different. I never realized that we will have that opportunity to work with our partners in Berkeley to be able to do, advanced research on several fields or several topics. And now that we are here, let's take advantage of this opportunity that we can learn from them, and also from the perspective of the Institute. Let's also use the Picari model so that we can use our knowledge to be able to share it with our local partners as well. So with that, I'd like to thank everyone for being here, and I'm looking forward to a productive day today. That's all. Thank you.
Thank you, Richard, for the message. And for the opening remarks for this morning's workshop, Dr. Roel Atienza, the project leader of PICARI AIRSCAN.
Okay, good morning. I'm Roel Atienza. Today I'm going to first give an overview of AIRSCAN. AIRSCAN actually is a project, PICARI project, Cycle 3 of PICARI. There are two teams here. We have the UP Diliman team and the UC Berkeley team. The UP Diliman team, I'm the project leader. Randy is helping me with the execution of the project. There are about 20 plus in our team. Half almost graduate students, half undergraduate students. On the UC Berkeley side, we're fortunate to have Claire and Alan here, who are the principal investigators at the UC Berkeley side. They also have a team of graduate and undergraduate students. AIRSCAN actually is a short name for Collaborative Area Robotics in Large-Scale Urban Infrastructure Management. This one started in May 1, 2017, and is about to end on April 30 to this year. Hopefully we can extend for one more year. Just to give you a quick historical background on this, the first email I sent to Alan, because he was looking for a collaborator during the time, was February 15, 2016. And the next day, February 16, 2016, we agreed to work together. So it was really fast. Then we submitted the first draft of proposal 2 weeks later, March 3, 2016. So really fast, okay? So then we started the year later. To give you a quick overview of the project, we can summarize this overview and objective this way. We want to create, we want to safely fly aerial drones in an urban environment and perform 3D reconstruction of a large infrastructure. So the key elements there are, number one, drones, and then number two, we should be able to safely fly it and then collect images and then perform 3D reconstruction. And it has to be a big structure. So I consider AIRSCAN to be made of 3 pillars, okay? And under these 3 pillars are the project leaders and principal investigators. We have on the safety control side, Claire is going to explain this in a bit more detail, making sure that when the drone is flying in an urban environment, it's going to be safe for humans. Then we have the VR interaction, VR user interface, which Alan is going to explain in more detail. As you can see, if you're going to fly a drone in a big structure, most of the time you will not be able to see the drone. So you need a way to see what the drone is seeing or to guide the drone. So in VR is a tool. Structure, we can collect images, and our task in the PH side is to create 3D reconstruction. So some people wondering what's the application of, or what are the applications of AIRSCAN. I can list down 3 key applications here. Number one is you can use it for monitoring construction projects. In fact, last year I was talking to DPWH director for monitoring, and then he mentioned to me that one of the key challenges of DPWH is monitoring the projects in remote areas. So typically they send the engineers in the remote areas and take pictures. And he said, it's even better if you can, we have a tool that can perform 3D reconstruction. So we know the extent of the progress of the project before the DPWH. DPWH, by the way, is a government department that is in charge of public works. So before they pay the contractor, they have to ensure that they completed the projects. Then, of course, we can use the AIRSCAN for preservation of historical sites. We can use this to create 3D models that we can use in VR or in 3D games. So basically, that's it, the overview of AIRSCAN. And we have Claire and Alan, we will discuss this in more details. And then after the coffee break, I'll come back and my team is going to present what they have done so far. Thank you.
Thank you very much. So we'll start with one of the two talks from our special guest from UC Berkeley. So allow me just to give a brief description biography of Dr. Allen Yang. Dr. Allen Yang is a chief scientist at the Home Institute, executive feedback. Yeah, as I was saying, chief scientist of Home Institute, executive director of the college. Center for Augmented Reality, Augmented Cognition, and lead researcher in augmented and virtual reality. He's a principal investigator at UC Berkeley and a co-founder and CTO of Crafty Incorporated. Previously, he served as CTO and acting COO of Athir Incorporated. His main research interests includes high-dimensional pattern recognition, computer vision, image processing, and applications in motion segmentation, image segmentation, face recognition, and sensor analytics. He has published several books, chapters, several journal papers, and many conference papers on these topics. So if Alex ready, so
Dr. Ali.
Thank you very much. So really glad to be here. Actually, I was thinking that I should be the last one to speak because so it's really, as you will see in my presentation, it really connects very complex algorithms, including drone control and 3D reconstruction, and being able to present that information intuitively and natively to the users. So to this end, and I will also say that I think this talk will be also, I hope that there's a lot of echo here. I don't know if I should stand here, is it better, or is it better to stand here? Or? I think that there's a lot of echoes here. So anyway, I will try to keep it a little bit further from my mouth. I hope that what we are going to talk about today may be also relevant to most of the people. So when you talk about this, you guys really have a dual role here. Number one is I'm sure that all of us actually are researchers. We are engineers. We deeply care about the technology. But at the same time, I will also encourage you guys to switch role as users. What do I mean by users? Can be your sisters, your brothers, your parents, your grandparents, right? And Roel just talked about, potentially we can use drones and 3D reconstruction to scan the buildings, to scan your game room, and so on and so forth. And what we cared about for, this sub-module of the topic is how to be able to design an interface that normal people can use it. I think that's really the goal and the power of the user interface. So today I'm going to talk about collaborative human-robot interface. And in this case, so when you actually try to do that, and of course you want to preserve the safety, and then you also want the system to be effective. I don't know how many people actually try to scan a building. So if you really scan a building by yourself, either you're going to put the camera on the ground, and then you just let it spin, and then you move it, and then you do a scan again. So it's really not effective. Now, if you want to use drone, and now you have to be, at least in the US, you need to be a licensed pilot. You need to be able to fly that. So how can we actually make that more intuitive for users to be able to do that? And can we do that in a semi-autonomous way? Or in the future to be autonomous, right? So I think that is one of the things that we are going to explore. We have explored together with the Philippines team, really, productively for 2 years, and I hope that so we can actually continue this conversation either in this project or even outside this project. And the second one is collaboration. In addition to scanning, I also want you guys to broaden the scope of the work to other type of interaction with the robots. It can be interaction with the humanoid, and can be also interacting by simply, allowing your parents to be able to, catch a package delivered by a drone from Amazon or from any other delivery companies in the Philippines, right? So a certain type of collaboration needs to be done. So our project is a collaboration with the Philippines team, and also in my group we have a large number of graduate students and undergrad students, and not all of them are funded, but in here I'm just mentioned even just the key members. We don't have the space for everyone, including Joe Mankey, David McPherson, Muhammad, Jean, Jesse, and Patterson. The last three people are undergrad students. Okay. As I mentioned, if you want to deploy a robotic system in the world, traditionally it will be, what you are going to have is typically a closed loop system. It starts with the digital world. You are a programmer, you are an engineer, you program some functions that ask the robot to execute. And then the control program is going to issue command to change the dynamics or the kinematics of the system. And then that will affect the physical world, right? So that pass. And when you affect the physical world, of course, you want to have certain type of observation, how your behavior caused the change of the physical world. So therefore, you also have perception, by certain sensors. So in that case, you observe the change of the environment, a change of the human in the world, and then you feedback to the world, feedback to the digital system. Now, based on that the input, perception input, you potentially want to change the behavior, whether you are driving a car or you are collaborating with the robot. In this process, humans play a significant role in both changing the control and perception. Just to give you a quick example, and you know that I think in the US and many other world, autonomous driving is really a big topic. No matter how much you have heard about autonomous cars crashed in highways, there are a lot more cars crashed by humans than autonomous cars. So the safety and then the perception and control of the human play a much more important role to the behavior of the system, at least for now. Maybe in the future, the cars are all fully autonomous. There's very little human input. But for now, actually, human input is actually a huge part of the factor that changes the behavior of the system. So talking about that, so that leads to a key observation that I want to point out is that having a really good human-robot interface currently is a pain point for using robots in man-made environment, especially domestically, when humans and robots are sharing the space. So that actually was not the case in industrial robots, right? So industrial robot in here, I'm just giving you an example. The first industrial robot I can trace, on Wikipedia was 1961, called a Unimate. And then from this picture, you probably can see that it's just a robot playing in the assembly line, putting some merchandise into a packing box. Now, fast forward more than 60 years, if you walk into a typical factory with robots in their manufacturing line, so this time of this situation is the one that you will see. So you will see that after 60 years, the interface itself hasn't changed. When you look at the machine, either today or the machine 60 years ago, you have no idea what they are doing, right? So, and how to guarantee safety and how to guarantee better control? Well, in terms of safety, the same old thing. You build a fence around the robots, and then you say that you are forbidden as humans to walk close to the robots because you may hurt yourself because humans don't understand what the robots are doing, and more importantly, robots don't understand what the humans are doing, right? And to this part, there is a famous, confession, so to speak, from the CEO of Tesla. Now, Tesla is arguably, one of the best car companies and forward-thinking car companies in the US. And he tweeted that last year, in the process of pushing out their new Model 3 cars, they made a mistake. So the mistake was that he envisioned that in order to make the cars more effectively and safely, he wanted the entire assembly line to be controlled by robots, as little human interaction as possible. And then they realized excessive automation at the Tesla factory was a mistake. In fact, humans are underrated. So there are many cases that we still need humans to collaborate with robots. If you really, based on today's technology, you completely cut out the humans, in fact, you actually will compromise safety and compromise the efficiency. Okay, so that is the background I want to set up. Now, how to address this problem? Well, traditionally, one way to do that, I mean, totally valid, is that you build humanoids, right? So you give humans a artificial face and some kind of display, and then they can very closely communicate with the humans. So we actually, in our group, we actually have a paper that really discuss about in a one-on-one conversation setting, if you have interaction with a human, with a real human. So there are 4 key cues that will really encourage productive conversation or collaboration. Number 1 is expression, a micro expression. And the second one is head pose. And the third one is gesture, and the fourth one is body scale. Now, we don't need future technology to give you a subset of this experience. In fact, what we are doing today, using Zoom, using Skype, actually encompass the first 2 parts, right? So if you can capture my face, and then you can capture my head pose, which means that you know what I'm looking at, my attention. So this is actually the traditional teleconference. But in addition to that, if you add gesture, and then you add the body scale in real world, in real size, right? So if I am not physically here today in the Philippines, but I'm actually in Berkeley, but in the future, imagine that I can virtually be here, but it is a full-scale human, and you can see my gesture, and then you can see my body, and that is the immersive experience, right? So that will be enabled by AR, VR, augmented reality and virtual reality. Now, if you want to scale back, we already have it, right? The teleconferencing. So you have a big hat in front of you, and then you hear people talking, right? That's teleconferencing. Now, I'm not saying that that's not valid. That has been, the driving technology that people do virtual conferencing for the past 20 years. But what I'm trying to say is that there are actually more that we desire. And then let me just keep on a little bit more about the literature review. So this actually is talking about collaboration. But the most important, most popular user interface is when the people are in control. So typically when you are driving a car, right? Arguably, at least in the US, there are more chances of people driving cars and then people doing teleconferencing. So that's the reason actually the country as a whole still spend the majority of the energy when people do business has to be on transportation. People still have to drive instead of relying on teleconferencing. So the reason actually going back is because teleconferencing cannot provide good gesture and body scale and head pose. So in that case, so in the driving case, the human in this role is a driver, a pilot, right? A supervisor, so to speak. So in this case, the car industry has already provided us the user interface that like this, right? So you have a windshield, and then you use the head-up display. It's also a type of augmentation to augment the GPS location, your car speed, and so on and so forth. And this has been proven to improve the safety of the car. And also it's intuitive, right? So if you buy a BMW, you buy an Audi, they are everywhere. So anybody, your grandparents and your parents, your sister and brothers, they can actually option to buy this. And there is no technology difficulty, right? So this is for supervisor. Now, there is additional role when the robots and humans are interplay in a typical conference. Continue to imagine that you have an autonomous car in here. Now, you may actually, as you are a driver, you have one car and then necessarily you may have one driver. But as you drive around the city, you are going to encounter a lot more people who are passive interaction users of your system, right? They are pedestrians. They are just minding their own business. They don't actually necessarily care about what you are doing. Now, if you are driving a car and this car is autonomous, how can you convey the same safety to pedestrians, right? We know we know what we do as humans. At least in the US, I'm sure that in a lot of areas in Asia, it's the same, right? So if we want to make sure, if we are pedestrians, we want to make sure that the car approaching me is safe. I can do 2 things. Number 1 is I establish eye contact with the driver, so I can actually get a sense of safety. And even better if the driver can wave me saying go, 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 and I know that I'm okay to go, right? But in an autonomous system, in here the car, and then you can imagine even worse, drone. if the drone is flying left and right from you, how can you make sure that the drones are safe? And making sure the drone has already detected you, and the drone will yell the right of road to you. Well, for Mercedes, when they actually announced their F350 autonomous cars, they thought about this problem. Because you have to provide this problem in order to make the car to be fully autonomous. So in this case, it actually does a real-world augmentation of a virtual pedestrian line. So when the car is actively illustrating a pedestrian line, the pedestrian actually, without any training, right? You cannot ask people to read a manual of the car for them to interact with the car. But if you can make the intuitive so easy that pedestrians actually can understand instantaneously that I'm safe. I think these are really the goal for a good human-robot interface, right? So to summarize, the challenges we have is, once in the future, near future, we can see that their autonomous systems and humans are really in close quarters interaction constantly in a shared physical space. The humans may assume three very different roles. At the very least, they can be passive users. So they are pedestrians. They are minding their own business. They can be supervisors, which means they are really in control of the car, of the system. And the third one may be collaborators, which means that there are certain tasks that are so complex, neither the human nor the robot by themselves can best or effectively do that. So we need to actually design algorithms to do that collaboratively. Actually, the collaboration is actually the main theme for this AIRSCAN project. So our hypothesis and our direction moving towards is to be able to develop a media that can flow the information smoothly between the humans and the control and the perception. So our thesis is that new enhanced reality, including virtual reality and augmented technology, will be able to fill this gap. The traditional technology will not be able to do that, right? Why do we say that? We're actually not the first person, the first team to sing this song. I can give you a example. In 2015, when Microsoft launched HoloLens, right? Probably many of you have heard about HoloLens. It is an augmented reality headset. Then you can wear it with you, and then you can virtually see the information. You can probably, by taking a second look, you can fairly easy to guess what is real and what is not real in this environment, right? So this tiny robot, that really bare bone robot, has wheels and 4 LED lights, is real. And then the the cabinet, and then the floor, and so on and so forth, and the wall, they're also real. But other than that, all the other information, animation there, that is actually not real. And think about that, it's quite amazing, right? Because Microsoft by no means is a main driving force of robot companies. They are not. But however, when they announce augmented reality solution, the first time, they are not announcing that for doing Office. They are not announcing that for playing games alone. But actually, they are illustrating, the best new application for augmented reality, which is to build an interface for robots. So in this case, either it is a ground robot or an area robot, and you quickly realize, number one, the robots are moving, right? So the difference between a computer and a robot is computers stay on the desk. It's not going anywhere. But the robots, they are running around. When the robots are running around, and how do you interact with them, right? So in here, if you don't have augmented reality, all you can see are 4 lights, two green and 2 red. Green means the forward direction, and red means the rear direction. But that's it. You don't know it's a battery condition. You don't know what kind of task they do. You can query that from command lines, right? So you establish a TCP/IP, and then you just query that. But your grandparents may not be able to do that. Your parents may not be able to do that. Your younger sisters and brothers, they don't want to do that, right? And how do we do that? In a more intuitive way, for normal people. I think that is the same vision that Microsoft shared with us. Okay. So this video, in fact, is widely available on YouTube. And in the interest of time, I'm not going to actually play this video from Microsoft. But if you really want to, if you haven't seen that, I will actually highly encourage you to do that. It actually shows you a dynamic path planning example that is very similar to what we do in controlling drones. Now, if I can have time to spend one slide, it's actually also very interesting to know that last year, 2018, is the 60-year anniversary of virtual reality and augmented. So the first virtual reality prototype was invented in 1958 by Morton Halleck and called Sensorama. So what that machine did was actually simulate allowing a user to drive a motorcycle on the street of Brooklyn. So it can simulate vibration. So the chairs and then the handle are vibrating. And it actually, like a street, a game, right? A gaming machine. And you put your hands inside this machine, and then you see the virtual street of New York and Brooklyn. And it plays sound of the street, right? So you have a feeling that you are virtually there. And in fact, it actually had even something more than the current commercial system didn't have normally. It actually has a smell simulator. So you can simulate the street of Brooklyn. Now, I'm not sure if you prefer that or not prefer that, but it shows actually 6 years ago, researchers, when they envisioned what a virtual being there, this thesis can be made, they have already think about, stimulating a lot of senses. Now, the only thing that it doesn't sense is taste, right? I don't know if you want to, put a sensor into your, tongue and then simulate some taste. But these are really the 5 senses that, at the end of the day, a virtual immersive experience will actually give you. Now, in 60 years, there are up and downs of AR and VR. Sometimes people really are, enthusiastic about that, and sometimes it's really a downtime because, there's a lot of money getting into that, and agencies and companies have not seen a significant outcome out of the research. But I'm happy to say that I have seen that since 2012, especially passing 2015, when Google and Microsoft are jumping onto the train saying that we are making AR and VR, we actually, at least in the US, have seen significant research funding increase in exploring AR and VR in applications. The reason is because in the past, before 2010, if you want to do AR, VR, you have to spend a lot of money, government money, for making the headset. Yeah. So you put a lot of money without any outcome. But now the companies are picking up the tag. So you can get really dirt cheap devices for less than $1,000, and then you can deploy that on your applications. So you have much better return of investment compared to 2010. So that's why actually you see more and more, at least in the US, government agencies and companies are funding AR, VR research. And we are actually very fortunate, actually built on 2 of Pickery. And then we actually received some continuation requests from companies like Intel and NSF, and also Office of Naval Research and DETRA for using some of our vision that we have actually developed in this project to actually solve some of the complicated problems that are relevant to U.S. government and the industry. That actually also is a testament for the vision of the system of this project, right? So we started 2-3 years ago, and even the U.S. government are so impressed about what we are doing. They want to actually try to encourage us to deploy what we do in their applications. Right? And also, at Berkeley, also we want to acknowledge that HTC Vive, either you guys know about HTC as a phone company or Vive as a VR company. They actually made a major donation to our center. So we are rebranding. We have rebranded our center as a Vive Center that really trying to use enhanced reality for different type of applications. So I know I was told that I have 45 minutes. So in the next 30 minutes or so. So that is my overview slide. I'm going to dive deeper into 3 areas in Berkeley that is started from the question of what kind of human-robot interface and interaction should be developed for interacting with drones. And then we actually branching out to a sense of optimality. From what is crossing the bar that should be there to the question of what will be the optimal way of interacting with robots, right? So we have to do that step by step. So we have to set the ground floor that make sure that at least in virtual reality, we are not compromising safety. We are not compromising efficiency, right? So once we set up the bar, then we can actually open a new door, and then we can pursue how do we actually make it even better, right? And I think that our project is only for 2 years, so I think that I hope that I can say that we have been successful in establish a ground floor that proves that for normal people without too much engineering experience or at all, and also a drone is not a drone pilot, can fairly safely and effectively control drones and perform tasks in a virtual reality space. So I hope that we can actually establish that as a basis for our conversation. And then, we are actually moving forward, going beyond the original core of this project, and then to investigate what should be the optimal way of designing the interaction with the robot. So, if there's a chance that we can continue this project, it will be fantastic. And we are also another commitment, from the Berkeley team is that we are putting everything that we have in here as open source. So regardless of the direction of the future, we as a whole can always, join the open source project and collaborate on the internet. So let me first show you a video of the first version of the system that connecting a human user in the virtual world to set waypoints for drones, and then that command being sent to a server, and then the server will issue low-level control path planning commands to the drone. And then you can imagine that, you can see from this video that, so the tight integration between 3D reconstruction and then the human interface, and then the drone control is very vital to the success of the experience. So this is our student, Jesse. And he is actually in a physical space, although he cannot see that. But you can see that what he sees is the right-hand side. He sees a low-resolution 3D scanning of the world. Now, I have to first say that we are doing divide and conquer, so you see that the utility of the 3D scan. So the user being able to, in the virtual world, being able to zoom in and zoom out, and still have an awareness of where the drone is, right? So in this case, we are actually using a Microsoft Kinect to scan the room. I'm sure that the Roval actually has a lot more higher resolution 3D reconstruction capabilities that you are going to hear today. For the purpose of this demo, we just use a commercial system to scan the world, and you start seeing that components of this project being integrated. And so these dots in the 3D on their waypoints for accomplish the goal to avoid the obstacles that we set in the virtual world, right? So just to increase the difficulty of this problem. And the system set the waypoint, and the pilot in the virtual world click go or launch, and then the lower level control will be able to execute the plan. So this actually is from Claire's group, being able to finally execute that on the left-hand side, okay? So you already see that a integration of the 3 modules play an important role in the execution of the plan. So the ISAC system has 3 different levels. The low level, we rely on the safety and the effective controllers from the control module. And then we build a ROS network to be able to communicate the information between the user and the drone. And then at the high level, we can take the 3D reconstruction model either offline or even online as the drones are scanning. I'm going to show you another video. And the user can, in real time, set pathways and commands, waypoints and commands, and then can execute on that flight plan, okay? So I know that you're going to hear from 2 other talks from Claire and Roel about 3D reconstruction and the low-level control. So today I'm going to actually focusing on the high level. Now, before we can get there, so I will just spend 1 slide to talk about the network. So in this case, we use ROS system API to connect. We also, because this is an indoor experiment, so we actually cheated, and we use a motion capture system to do the localization. Now, in the real world, you are going to use, if it's outdoor, you can also cheat it. You can use GPS system. So you don't actually have to care about, at least for the localization. But you still have to care about the orientation. I'm going to actually talk about a little bit about that in the later stage. But if you have a multi-system, you can actually get the 6 degree of freedom in an open space fairly cheap. And then you are going to get the packet from the optic track system, and then it will upload to the ROS system. So the ROS server will know in real time, fairly fast, where is the location of the drone or a fleet of drones. And then that location also being shared by visualizing a virtual drone in the 3D world. And then the user will be able to change the behavior of the drones in the virtual space. So as I said before, at the beginning, we really want to establish a baseline, right? Before we run, we want to know that we can crawl, we can walk, right? So it's really true that a basic virtual reality system with the basic functions of just flying the drone. Forget about scanning, forget about deliver packages for Amazon, and just for flying. And then for normal people, for your grandparents, for your parents, for your sisters and brothers, without any training, will they be safe? Will the system be safe under their command, right? So we designed a user experience experiment. So we enrolled 12 subjects, and then we put them into this virtual reality system. And then we asked them, of course, if they're not just flying the drone, that's too easy, right? So we set up alternating obstacle courses. And then we asked them to be able to fly to complete the pass, and then using 3 modalities. Number 1 is user controller, right? So the traditional game controller. Imagine that you are flying a drone as a competitive pilot today. And the second one is the 2D interface. So that is the typical 2D interface. If you have an iPhone and you plug into a DJI drone, and that's the interface you have, right? So that's the bird's eye view, orthographic projection, from orthogonal to the ground, and then you can sense the X and Y direction, and where is the Z direction, right? So the height. The height typically, when you click a point in the 2D direction, it actually pops up a number. So that will tell you the height of the terrain, right? So that's the 2D interface. And of course, we will also let them to try the 3D interface. In the 3D interface, everything is intuitive. You actually turn your head, you can actually see from the left and from the right of anything you want to change. And then we ask each user for 3 trials for each obstacle course, and then each subject will spend about 1 hour in our user test. And we measure the number of crashes. And then we also measure the number of time that flight can be completed. And then we compare the safety and the efficiency, right? It turns out actually the results are even better than we imagined. So this is something with a solid validate hypothesis, right? So the hypothesis number 1 is the VR path planning is safer than manual control. So in our experiment with 12 human subjects, there were 24 crashes if you fly the drone manually, but there were only 2 crashes. Imagine those people are the same people who has no experience of a drone flying, and then there's no experience about virtual reality for flying the drones. So there are only for 12 people, and in 1 hour, so it's in total about 12 hours of 12 different people, there are only 2 crashes. So that's actually is amazing. And we also calculated the statistical significance about that, which is using the p-value, is the probability of the failure of the hypothesis based on the data, amount of data you use. The p-value is extremely small, right? So 0.001, which means that with high confidence we can say that VR path planning is safer than manual control. And then you can also see from the bar over there. So if you calculate the mean and then the standard deviation, you can see that the second one is the manual interface, and then third one is VR. So they are not even overlapping. So that actually shows a high confidence that the VR is safer than manual control. And how about the efficiency? So in this case, we compare the VR path planning to the 2D interface, right? So that is the industrial standard currently if you fly drones such as DJI. So in this case, they are equally safe, if you plan carefully in the 2D interface, but the difference is time. When you plan in VR, it saves you every pass. Remember, this is a really small lab space, and Roel and your team actually were in our lab. You know how small it is. So there is a 1 minute difference in planning the pass in the 2D interface and VR interface. So people are planning and more effectively observing the behavior of the system than the 2D interface, right? And the same, the p-value is less than 0.001, so which is also very significant. And then you can see the mean and then the standard deviation of the 2D interface and the VR interface, right? So the two bars, they're not even intersecting. So the difference is clear, right? So this actually is the report that we are submitting to the UIST currently. And going forward, as I mentioned, that this is really the baseline we want to establish. What we established that the VR drone interface is safer and more intuitive than the manual control and 2D interface in waypoint-based navigation. Now, so there's a lot of imagination you can have, coming out of this research. Is that the waypoint-based navigation probably is too easy, too simple. We want more realistic tasks. Now, some of the tasks are search and rescue, right? So what happens if your terrain has changed? Then you need to scan the terrain live. Either you have a power plant, you have a fire, or you have an earthquake. You really want to send the drone first because they are fast to go there, and then you are not risking rescuers' life. And also, for commercial use case, you are thinking about warehouse delivery, right? So in the US, I think that's probably the #1 use case people are thinking about using drones, for helping companies like Amazon. And the second one is multi-drone fleet control. Instead of a single drone, what happens if you have a group of drones? Is there a ceiling for the capacity of a human? If you go past this capacity, the human performance will go down, right? And then finally, in terms of legally and financially, the highest pain point for drone, the ceiling for drone is currently in the US, the legal system, the US law does not allow out-of-sight drone flights that really limit the capability of drones. So how can we use virtual reality? If we can prove that virtual reality are safer and more effective for more meaningful tasks and for monitoring multiple drones, is it possible for us to convince the legislature in the US to allow in the near future out-of-sight drone flying in urban environment, right? These are, I think, the really exciting future points, pain points that we are actually exploring. So let me actually show you just 2 videos that illustrate we are heading this way. So this is a video that we just got last week that is a collaboration with the nuclear engineering department. So in this case, imagine that you have a collapsed nuclear power plant, right? I'm not going to say what is real, what's not real. And because the building has collapsed, so when you fly the drone, you cannot rely on the offline 3D reconstruction. You have to reconstruct the world in the real time, right? So you are seeing that a drone that carry the LiDAR scanning are scanning the world in real time. And in addition, the drone also carry a radiation detector integrated in the drone. So you actually see that the overlay of the radiation sources with the 3D reconstruction. Now, so this is the result you get from the drone. Now, when you have real-world rescue team coming in on the ground, when they wear something like HoloLens, they can actually overlay that most important information about the radiation on their head-up display. So they will actually know where are the radiation sources beforehand, so they can avoid those areas, right? So that will actually really save time, and save rescuers' time, and also save potentially victims' time, right? So this is a more complex text. So we are already working with some other funded projects. And the second one is extending our project to multiple drones. So we are able to already expand the capability of our system to do that.
To get an overall view of the scene. Outside of the scene, there are 3 magnifiers. Users can rotate the scene by controlling the right thumbstick. And can also move forward and backward using the left thumbstick. To complete a task of climbing hoop jump, we set 2 hoops and 2 drones in the scene. In the Unity interface, Users are points for that drone. In this case, we're generating the first half of a heart. By clicking the right-hand trigger, user can deselect that drone and also place a new.
So I really like this demo. So this is really showing the human side of controlling robots, right? Controlling robots to draw a heart and using the LED light, right? You probably, many of you have seen the Intel firework, right? So the coordinated show of LED lights in the sky, and this is what our student created in the lab.
We can see them take off in the software simulation. The lines represent
so for safety issues, we actually first simulate that in software, and then we put that on the drone platform, and then we fly it, and then we capture a long exposure sequence of the fly path.
Are they using fast track?
Yeah.
They
are using fast track.
Actual drones are launched to follow the shape of the heart.
And Claire probably can actually explain the execution, the planning of the path. Right.
Hardware simulation.
Now this is flying the drone in real time, right?
Two drones to fly through loops.
So we haven't gotten the solid results. Then the first paper yet, we're working towards that. As I mentioned, some of the things we want to push forward. But the purpose for showing you this video is to show you that our system works. Okay.
After the launch button is triggered,
and the lower left side is the real world execution of the drones. And then the location of the drones are being synced up in real time into the virtual world. So you can see in real time where the drones are. If the drone is deviating from your plan, you can always grab the drone and then ask it to stop, right? Okay? So that's the first extension, right? And the second extension is to the interface itself, right? So in addition to say that, it is safer and it is more efficient compared to the manual control, right? Now we want to walk past that. We ask, if we are already in the virtual space or augmented space, what's the sense of optimality? How can we actually design a system that's better than the first virtual reality system? So in this case, the challenges in designing the 3D UI UX design and then establish a sense of optimality is because of several factors. The number one is absence of design standard for 3D UI. So think about that. Since the 80s, people have been using the keyboard and mouse to do 2D design, right? And so the methodology has been established, right? So if you are an application developer, you are app developer, you don't have to worry about the user interface, right? So the interface are provided to you as API, whether you are using iOS, you are Android, or Windows, and so on and so forth. But in 3D, currently there is no standard for 3D UI. Even worse, the problem for that, without a standard, is that if you have two teams developing the same function for controlling drones, it is very likely that if you use application 1, there's one way for you to control the drone. If you use application 2, there's a totally different way. So doing this transition, not many typical users can do that. So that is really the pain point for hurting the 3D interface. And the second one is a variation of 3D input devices. So in 2D, we have standard keyboard and mouse. Even if you play the fastest response games, you just use keyboard and mouse, you can get sub-millisecond response time. But in 3D, you have to actually use new input devices, like 3DoF controllers, 6DoF controllers, your gesture, eye tracking, hand tracking, and the voice. And these actually are not typical. And the third one is lack of haptic feedback. When you use keyboard and mouse, you actually have a plan that supports your arm. That turns out to be the very, very important. I'm going to say a little bit about that. And the last one is lack of resolution, limited resolution in design, right? So that actually is limited by the display of the system. If we have time, I can actually talk more. It's amazing the resolution, talk about the retina display, the human eye resolution. If you really want to feel every pixel that people can recognize from the eyes, the average display resolution has to be 8 times bigger than the current brightest cell phone display. So we are simply not there to give the so-called retina display in virtual reality. So in here, let me show you, if we have all this interaction integrated, what kind of experience we can have. So we're talking about drones, instead of flying drones, let's talk about maintaining drones, right?
Solution that allows 3D instructions to be overlaid in augmented reality.
Now first, you're going to scan this drone, right? So you have to have a scanned drone model. So as you're looking at the drone in real time, the system actually can resolve the location of your head, your display, relative to the drone. Once you have that, then you can overlay the module, the manual 3D model of this drone when you try to alter, try to make changes of this model in real world. Right? And then you can also augment a virtual expert to guide you in 3D. Right? So this is not reading the manual anymore. So this is really showing you holding your hand in the 3D world.
Right? The creation of precise annotations and intuitive visual cues. The goal of Pengram is to eliminate ambiguities that comes with complex operations.
Can you also illustrate what kind of tool that you need, and also set, you can set the parameter of the tool so that you don't over screw, put the pressure on your screwdriver and so on and so forth. And our system actually, received the 2018 Microsoft Imagine Cup World Finals, the only mixed reality award, and also actually is the only US team that received the award for that. So I see that I have 5 more minutes. So 2 more minutes? Okay, so let me actually do very quickly. We also have 2 papers published that really try to test the optimality of converting people from designing in 2D versus designing in 3D. And then you can see that across 4 different hypotheses, we actually win a lot in the intuitive department, ease of control, and then the mental frustration. Because reading manual in 2D is really frustrating. The only thing that we lose is in physical discomfort. There's still a lot of discomfort in wearing VR, but that actually is contributing to the VR system, right? So let me also mention in here, I think this is important, and then I'm going to quickly wrap up. And what we have learned are 3 things. This one actually is in collaboration with Siemens. Siemens was very generous and opened their workforce, and we're actually testing on their field engineers. So what we have learned is environment matters. When you put virtual objects in the world, where is the location of the object with respect to you in terms of their size and location? If the size is not the real size, and people have to do translation, and that actually causes mental fatigue. And the second one is if you put the object too far away from people, they are actually not within the arm's reach, people also are frustrated. So that's number 1. Number 2 is having a tutorial is very, very important. So I actually didn't emphasize that, but for our user testing previously, before the user started flying the drone, we always have a tutorial for them. In fact, if you ignore the tutorial and then you imagine, oh, virtual reality just as a real reality, you just put people right into the virtual reality, they don't get it because they actually get more about keyboard and mouse. If you tell them to control drones using keyboard and mouse, they actually learn faster than virtual reality. So in virtual reality, in the current stage, actually people, the learning curve is still a little bit higher. But once they get to know about VR in certain level, they really perform really well. And the last one, that's one that I want to come back, is the virtual reality currently is great for doing the supervision and review, but it's actually very hard to build objects. The reason is because if you want to build a precise millimeter accuracy object, because in the real world, you don't have haptic feedback, and then you always have this handshake. So drawing anything with millimeter accuracy in space is really, really difficult. And our advice is still using keyboard and mouse to design your asset in 2D. And when you actually can rest on the stage, and then you can use mouse and then to zoom in and zoom out. And then you can do people to experience that. I know that I don't have time to talk about OpenArc, and unfortunately, that's actually outside the scope of the project. Let me also mention that OpenArc is designed for measuring the humans, right? So the ISAX is about the environment, the drone. What about the human, right? So this actually is a separate project that we use wearable sensors to actually understand more about the human. That including the sensor fusion, calibration, 3D gesture, right? Instead of using controllers, now you can use gesture. And then we do offer a comparable room size SLAM. So remember I talked about we actually cheated to use the mocap system. But if you really want, you actually can also use our SLAM algorithm to do navigation, right? And then we also, right now, have a new module to be able to track human avatar. So if the drone happens to bump into a human, we can actually see in real time what the human performed. And this actually is in collaboration with Intel, Ford, Siemens, and the Vive Center. Okay, so this actually is a video of large-scale SLAM, and then you're able to just carry this very tiny sensor that's half the size of this, and then you can walk through this room. When you get back, the track actually go back to your origin, right? So that allows you to do virtual placement of information. So let me wrap up. And OpenR is also open source, so it's available online. So if you want to know more about it, so you can talk to me, and you can also check out our GitHub OpenR. So finally, let me just conclude that during the past 2 years, very close collaboration with our Philippines team and also with Claire, we come to an understanding that it's really important when we build interactive human tasks that has very complex algorithms for control and perception. We need to be able to hide those complexity and being able to present the information that we got as the result of this control and perception as simple as possible to humans. In this case, there are 3 roles humans can consume the information. They can be passive users, pedestrians. They can be supervisors, they are closely control the drones, and then they can be collaborators, actually want to add on to the capability of drones. And we believe that with the build on more and more functionalities in enhanced reality, we will be able to achieve these tasks in very near future. Thank you very much.
Thank you very much, Dr. Allen Yan. So please hold off your questions until we are at the open forum, so we don't have time to entertain questions at this point. So while Dr. Allen Yan was doing his presentation on, and also while Chloe is setting up, I had a question at the back. He said, what happens if there's obstacles?
You are the first person to join the conference.
We'll answer that question on safety control. So our next speaker is Dr. Claire Palmer. Just introduce her. So her talk is on safety assurance control. So Professor Palmer is Professor of Electrical Engineering and Computer Science at the University of California, Berkeley, where she holds the Charles A. Desswer Chair in Engineering. She held the position of Assistant, Associate, and Full Professor at Stanford University from 1998 to 2007. Gene, the wired one. I'll just continue. She received the Erlander Professorship of the Swedish Research Council in 2009 and MacArthur Fellowship in 2006 and the Ekman Award of the American Automatic Control Council in 2003. She works in hybrid systems and control with applications to air traffic systems, robotics, and biology. So please welcome Dr. Claire Palmer.
Thank you, Randy. Can you hear, or should I use this?
The wire is better.
The wired, maybe the wired.
Yeah, the
I'll
wire
use
is
the
better.
wired one. Yeah, it's a real pleasure to come and to visit and to also work with Roel and Randley on this project. So thank you, Alan, for giving that presentation, which also, I think, provides some very visual motivation for the work that we've been doing on this project in safety control. And I'd like to spend these next 40 minutes or so presenting what safety control means and the technologies that we've been developing to provide safety control in the context of these drones, of these unmanned aerial vehicles or UAVs. This is maybe even a little outdated now. I mean, this was from a few years ago, but now we see more and more drone applications of things that I had never expected. But this just ability to have these flying vehicles, maybe one of the most exciting developments is using these vehicles closely and around people to take pictures of activities, to follow you as you're doing some kind of sporting event, or to really be something that's sort of close by. And you know, on one hand, it's exciting. On the other hand, it's a little bit scary when you go to the park with your kids and people are flying drones around, and you know that you know, these are actually, if they fell or crashed into somebody, they could actually hurt. So there's quite a bit of motivation when you're using drones in and around people to have some kinds of guarantees about the behavior in terms of not coming within a certain distance of people or other drones. And so we, in my research group, we've been working in control theory for a long time, and we've been working in control of unmanned aerial vehicles for a long time through the context of automating air traffic control. So I've been working for 20 years with the American Federal Aviation Administration and NASA to try to understand what kinds of technologies are appropriate for putting onboard aircraft and in air traffic control centers to ensure that highly automated aircraft in the air traffic control system, now these are piloted aircraft with passengers inside, maintain a certain separation distance from each other. And so over the past 5 years, it's been very exciting, and we've received funding through grants like this, but also grants from NASA, to understand how you might take those kinds of technologies and apply them to automated aerial vehicles, so the kinds of drones that we're working with, or even larger drones. Okay, and so first of all, safety is important. Some kind of simplicity of operation, and Alan really talked about that very nicely. If you have a human in the loop, I mean, it doesn't necessarily have to be simple, but there has to be a fluidic way of transferring control between what is automated and what the pilot or the autopilot, that switch between pilot and autopilot. And then for drone operation, where it is much more autonomous than piloted aircraft, there has to be, you have to incorporate in that safety the ability to adapt to new information. So if these systems are automated, they're using onboard sensors typically to adapt to information that they're getting in real time. All right, so these are two companies that my students have been working over the summers in different companies in the Bay Area. The first is a company called Skydio. It's basically a bunch of flying cameras. It's a vehicle whose sole purpose is to transport really high quality cameras to be able to take really good images of the surrounding environment. The second is it's an automated vehicle company. They're fairly small vehicles. People don't fit inside. They're for delivering things. And so their Neuro is traveling on the same roads that automated vehicles that carry people are traveling in. So it really illustrates that, you know, we're moving towards a much more automated environment where that automation is going to be close by. And so especially considering safety with respect to people in the environment is very important. So in this next now 30 minutes, I'm going to talk about two things. The first is safety-based control, and the second, and some examples. And the second is how you incorporate adaptive methods, machine learning, into a safety-based control. So that, first of all, safety primarily, and then secondly, how do you allow these systems to adapt online to new information, but still maintain some level of safety, or kind of bookkeep what safety means. All right, so this is a tool, reachability, that's been around for a long time. My background's in control theory, and reachability is really one of the fundamental tools in control theory. In my research group, we started out, you know, when I started actually when I even was a student, I was working on these technologies, and then we built a research group around that when I became a professor. But the idea is this is for safety-based control, is kind of intuitive. So suppose you have a system, you've got an aircraft, or you've got a group of aircraft, and you define what it means to be safe. So in control, we have a system, we build a mathematical model of that system, and then we write a specification for what we'd like the system to do. I mean, we've known that from the beginning, but we have to be precise about that specification. And then what we'd like to do is, with the mathematical model and that specification, we'd like to verify that that specification holds for that mathematical model, or in addition, we'd like to design control schemes, so automation, which guarantees that that specification holds for the model with the automation in the loop. Okay, that's kind of the standard bread and butter of control theory. So here, specification is safety. So you have a system, an aircraft or a group of aircraft. You'd like to make sure that that system remains safe. Okay, so what does it mean to remain safe? For an aircraft, it means it stays within its flight envelope, right? It doesn't stall. You don't want it to fall out of the sky. You don't want it to crash. So it has to stay away from, ground and other vehicles in the sky. So for a group of aircraft, typically we care about collision avoidance. We want the vehicles to avoid each other. We want them to avoid other things like people. Okay, so suppose then you could take the model of the system, it's operating in some state space. You take that safety specification and you represent it as a region in the state space of the system. All right, so what does that mean? For a single aircraft, it means that you've taken the states, the velocity, the altitude, the positions, the angles, the angular velocities, the accelerations, and you define an envelope in that space that defines if the aircraft is inside that envelope, it means that the system is safe. All right, so the specification is represented as a set. For a group of aircraft, you do the same thing, but now typically your models are simpler. You've got maybe a few variables like the position, maybe the orientation, but in the relative coordinates of multiple aircraft, you want to make sure that the vehicles stay apart from each other. Again, that can be represented as a set in the system state space. Okay, so safety specifications is a set. That set, so in this diagram here, that red ellipsoid is my representation of what it means to be I say unsafe. If the state of the vehicle or the group of vehicles enters that red ellipse, G of 0, it means that the system is unsafe. And then reachability is simply the propagation of that set through the dynamics of the system. So what does that mean? It says that you've calculated all states for which the system could go unsafe. And that's that pink region, and it's indexed by time. So the set G at time t are all states, and it's a control system, and there's disturbances in the system. So the set of all states for which, for all possible control actions, there's a disturbance or under the dynamics of the system that could cause the system state to go into that unsafe set, to become unsafe. All right, so we needed a model, a mathematical model of the system. We needed a specification for safety, and we need the ability to do that computation. And those are typically, those are the three components that you're working with when you're working with safety-based control. But the idea is that once you've computed that set, then you can do all sorts of things with it. You can use it to verify that the system remains safe if it's outside of that region. So if it's in the region that we've colored in blue, it means that the system will remain safe for at least t time units, okay, because it's not inside the backwards reachable set. You can design controllers to keep it outside that unsafe set or that backwards reachable set. So the system can sort of meander around in the blue region, flying around, for example. As soon as it hits the boundary of the red region, you apply a safe control. Okay, so we've been, as I said, not just us, but there's sort of a community and control, computer-aided verification working on safety-based control. In computer-aided verification, it's called model checking. You're checking a model against a specification, and we do it using reachability. In my group, we characterized for a control system how you represent these sets and how you compute these sets using optimal control. And so the idea is to compute these backwards reachable sets in an iterative manner by solving an optimal control problem, which is, it's a variation of a very old standard optimal control problem coming from what's called Hamilton-Jacobi theory. And so there was work that we did in my group in developing numerical tools to compute this. But the theory is sort of stands from a long time ago, and it's a very classical theory. We use what's called a level set interpretation. So we represent sets as functions, as zero level sets of functions in a higher dimension. And then instead of representing and propagating the set, we represent and propagate the function, and then we always capture the zero sublevel sets of that function, and that represents the set that we're interested in. So that's an efficient way, and it has some mathematical elegance to it, but it also has some computational advantages. Okay, and then you've got other things, like if you've calculated a reachable set, then you know that any super zero level set of that can also be used to verify safety. So if you've computed a set that you don't want to get into, if you don't get into any over approximation of that set, you're not going to get into the set itself. And that's useful. And then the more you know about the dynamics and the uncertainties, the less conservative the set is. Okay, so we've developed a methodology for computing this and a toolbox. At the bottom, there's a web link so Ian Mitchell was my first PhD student, and now he's a professor in Vancouver in Canada at the University of British Columbia, and he took those mathematical concepts and he wrote a toolbox, and you can download this, open source, freely available, wonderful. He's great at commenting and writing manuals, so there's manuals, you can pull out his examples, plug in your own, and do this computation. Okay, so this is one of the first examples that we ran. So on the left is, these are old quad rotors. These are when I was still at Stanford, and you couldn't buy quad rotors then very easily. You had to build them, so we built our own. So there's 4 students and there's 4 quad rotors, and each student is joysticking a quad rotor around, and they're trying to crash. And when the vehicle comes within the reachable set of another vehicle, the automation takes over and guides the vehicle away from each other. And then when they're away from each other, the control is given back to the student pilots. There's not a video on the right. I'm not sure why it's not playing. But the data playback is on the right, showing around each vehicle the reachable set with respect to the 3 other vehicles. Okay, so that's going on in real time. Pilots are trying to collide the vehicles. Those sets are being computed in real time. When a vehicle touches the backwards reachable set of another, the automation takes over and guides them away. So that was kind of a first proof of concept that we did. You can also use this technology to not only avoid unsafe regions, but get into desired regions, so capture a desired set. Same methodology. In the control problem, it's just flipping a min and a max, so you're trying to get the control to get you to a set instead of avoid a set. And you can work on hybrid versions of this, where you have different control modes, and you're switching between modes. So you'd like to reach a target, you may have to go through a bunch of different modes before getting to that target, but at the same time you also want to avoid an unsafe region. So we call that a reach-avoid operator, all computed using this level set technology, how you get to reach a desired region while avoiding an unsafe region. Yeah, so Alan mentioned package delivery. This is a big thing that Amazon has been working on. And so here, this is just a map of where we live, the kind of North Bay area. You see San Francisco there, and you can see sort of these regions around the San Francisco and Oakland airports. So we mapped out from a warehouse in Concord points to various Bay Area drop-off points. And then we did a shortest path algorithm where the idea was that flying over heavily populated regions, flying over airports is very expensive. You don't typically want to do that. Flying over the busy kind of city-based areas is expensive. Flying over lightly wooded areas, kind of forests and stuff, is cheaper. And then flying over water, which is the yellow, is the cheapest. So then the shortest path algorithm finds a route which is basically mostly over water, making short deviations into heavily populated regions for pickup points. And we worked with both NASA and Amazon on so now it's like air traffic control, but for drones. So it's called a UTM, Unmanned Air System Traffic Management Algorithm. And kind of the interesting problems are, what is automated? What is human controlled? There's going to be much less human control in UAV control versus air traffic control. But how do we organize these groups of UAVs along these different kinds of routes that we've planned? And so we used an old routine called platooning. Platooning is an idea where you basically route a bunch of vehicles along the same route, flying at the same velocity. So they really only have to maintain separation with respect to the vehicle in front and the vehicle behind. And then you design a control scheme that ensures that that's safe. And we use reachability to design the control scheme, to basically figure out when you should switch from a free mode where the vehicle is flying off a highway, one of these highways in the sky, the trunk routes, to be a leader or a follower in a platoon. And then having a fault mode, which is either changing the altitude lower or higher. And so the reachable sets, so I'm going to show them for just a couple of different scenarios here, where here we have two vehicles, a red and a blue vehicle, trying to track a moving target on one of these highways in the sky and snap onto it. And so the reach avoid operator here, each vehicle wants to reach that target while avoiding the other vehicle. So we can compute automatically that reach avoid operator, and then the control is then automated based on that reachability based control. And as long as the system, the model is correct or over approximative and the specification is correct, then you have a guarantee of safety. So this is shown for two vehicles, and the control results in some kind of nice fluidic group formation. Here we're not showing the sets, but we're showing the vehicles in different colors, snapping to that moving target on the highway. If a vehicle is not following the rules, so it's an intruder, and it can be accounted for. A much wider berth is automatically given through this algorithm, so the avoid set becomes a lot bigger. The vehicles actually depart from the highway before they rejoin. There's a lot of interesting problems around reachability and safety-based control, which have to do with a problem that I think we all have dealt with, which is the curse of dimensionality. When you're solving a problem like this, you're computing a region of the state space which has a certain property, say safety or unsafety. You have to do that computation for every point in the state space. So that requires you to grid up the state space, and the more dimensions you have, the more grid points you have. And so it's basically very simple. The computation grows exponentially with the dimension of the continuous state. So a lot of the research in the community has been on how to do these computations faster, how to make some approximations, how to make some simplifying assumptions on the engineering problem itself so that you can do these computations online. Platooning was one idea. Basically, as I said, if you have a bunch of vehicles and you have to compute your safety-based control with respect to all of them, that makes the dimension of the state space very high. But if you can organize the flow of traffic, like we do on the roads, through highways or platoons, then you've limited the number of vehicles that you actually have to do the safety specification with respect to. So we've done a couple of things here, but I want to mention one of them because it really falls into what we developed as part of this Picari project, which is the idea of fast track. So how might you use a safety-based control in real-time path planning? And so this is the tool that Alan mentioned his group has flown when doing that UAV flight through the hoops using the AR/VR interface that his group has developed. So the idea here is that you'd like to plan a path for a vehicle through an environment possibly unknown, where you don't want that vehicle to like hit anything in the environment, and that could be other moving obstacles, but right now let's just assume that, or people, but for the time being, let's just assume in this first development that those obstacles are static, so they're not moving around. And let's suppose that you can sense those vehicles in enough time, and we'll talk about what enough time means. So you have a sensing berth, which is enough. What you'd like to be able to do is plan paths safely, and robotic path planning is a field that's been around for a long time, and typically what's done in robotic path planning is this kind of thing on the right-hand column I have on this slide. Fast but not very accurate planning. So all these really, really popular and great algorithms that are kind of building probabilistic roadmaps, for example, where you have a space, you put a bunch of points, you connect those points with lines, and then once you get a line that goes through an obstacle-free area, that becomes a viable path. I mean, that's the basis of A*, the basis of RRT, the kind of most popular robot path planning algorithms. And they work really well. However, when you're actually flying something, they're not just flying on lines connecting points. They're flying dynamic trajectories because the things actually have dynamics. And when you're driving, it's the same thing. So in robotics, the way they account for that is by putting a buffer around obstacles, making the obstacles bigger than they actually are, and then doing the fast planning. But how big do you make that buffer? And so really what we did here is we used reachability as a principled way to compute that buffer. And the idea is actually kind of intuitive. You have your dynamic model. I don't know, for a quadrotor, we typically use 12-dimensional states for this. You've got your 3 positions, your 3 orientations, your 3, and then the derivatives of those. So velocities and angular velocities. So a 12-dimensional model. But for RRT or something, at best, you're going to be using a 3-dimensional point. The point's just moving, so it's just a 3-dimensional model. So there's a difference of like 9 dimensions between those. 12-dimensional, high-dimensional model, 3-dimensional point source that you use for fast planning. You don't want to use the 12-dimensional model for fast planning because then it won't be fast anymore. Okay, so you, ahead of time, you pre-compute a reachable set representing the biggest error between the 12-dimensional model and the 3-dimensional point source. And that's what this middle column is, the proposal. Pre-compute a maximum error bound between your 2 models. You know what your models are ahead of time. So pre-compute that bound and then carry that bound around with you for planning in real time. So it's what you're pre-computing is basically that buffer that's been, that's sort of been used in an ad hoc way in robotic path planning. So this is a sort of visualization of that. This is a visualization for a 4-dimensional model tracking a 2D point source. So let me actually go to the next slide. It's a little non-intuitive there. Well, actually, this is sort of non-intuitive in this slide too, but reachability is often a little bit non-intuitive. Because it's, as long as it's in position dimensions that you can see, you can kind of look at that and say, okay, I see that's a collision zone. But now these dimensions are angles and angular velocities, right? They're not something that's intuitive. You can see this, what's going on here. So what we did was we said, we have this function on the left-hand side that we're computing a backwards reachable set from. And that function is representative of the difference between a 4-dimensional model and a 2-dimensional model. On the right-hand side, we've taken slices of that set. Basically what we're asking. So here I've got 3 different slices. A radius of 0.5 meters, 0.75 meters, and 1 meter. So 3 different circles of different radii. And we asked, what is the largest controlled invariant set inside those radii? And if that largest invariant set has volume, that's the backwards reachable set. And it tells us that yes, you can maintain some distance between, you can maintain that distance of either 0.5, 0.75, or 1 meter from the other vehicle, from the other model of the vehicle, as long as you stay inside that control invariant set. So what this says is that with those 2 models that I had, there's no way to maintain a 0.5 meter distance from if you're using the 2-dimensional model and you're tracking with the 4-dimensional model. There is for a 0.75 or a 1 meter radius. So that gives you, as long as you stay inside those kind of funny shaped sets. But we can characterize those sets, and we have a control law that keeps us inside those sets. Okay, so what it does, and let's go to an example which is a little more intuitive. All right, so now I'm looking at something a little bigger. I've got a 10D quad rotor. So this is, it's not 12D because it's near hover, so I'm able to save a couple of dimensions there. And it's tracking a 3D point source. All right, so I'm doing planning with the 3D point source, but I'm computing a backwards reachable set based on the relative model between the 10D and the 3D, which is going to be a 10D model. I pre-compute that ahead of time, and then I carry around that set when I'm planning in 3D. And so that set is computed, as we just said, in 10D, but I'm showing a 3D projection down into the XYZ coordinates of that set, which looks like a little box. And now I'm taking that green star, and I want to plan over to the blue circle using that in the face of obstacles, which I'm going to sense as I get near to them. And I've got a buffer, a reachable set I've computed this buffer zone ahead of time that I'm carrying around with me. So now it's just as fast as, I'm using RRT here, so it's just as fast as standard RRT because I've pre-computed that buffer. So the obstacles turn red once they get within a sensing radius here. This is just a simulation, as you can see. So it's not done in real time. But as it goes through, I have a guarantee that the actual model will remain within that box of the green star, which is used in planning, as long as I trust the models that I used in computing this reachable set. So fast track stands for fast and safe tracking. Sylvia came up with that acronym. I really like it, fast track. And it's basically this idea of pre-computing, using reachability, that buffer zone, and then using it in real time for motion planning. This is just a shot to show that what is typically done, which is in control, which is design a path using RRT and then use some kind of linear quadratic regulator to try to keep your real system close to the planned path, is not guaranteed to keep it within the zone. Whereas fast track does, because of the fact that you've computed that buffer in a principled way. So now you can do all sorts of things with it. You can ask, you know, what if I had a bunch of different qualities of models? So I've got my 3D point source. That's my lowest dimensional model. And then I have my 12D model. That's my highest dimensional model. But, you know, maybe if I'm in kind of a wide open space, like in the front of this room where there's not much in terms of obstacles, I don't really need a 12-dimensional model. I could plan with, you know, a 6D model. And that becomes a lot faster. You know, I can compute that quickly. But when I'm moving up in sort of a narrow corridor, I have to be a little bit more careful. I want a smaller buffer. So the bigger the model difference, the bigger the buffer is going to be. So when I have a 12D model with a 3D point source, it's very accurate. So I'm going to get kind of a small buffer, and I may need that small buffer if I'm going through narrow corridors. So I can actually do real-time switching between higher dimensional models and lower dimensional models to go from smaller buffers to larger buffers. And so you can see this TEB stands for tracking error bound. That's the buffer that we're computing. And here we're switching from a wider buffer to a smaller buffer. It's basically going from a faster planner to a slower planner. Okay, so fast planning in wide open environments to slow planning in narrow environments, but always maintaining that safety guarantee. And what's more, reachability can tell you exactly when you have to switch, as long as you have the preview of when you have to switch from a fast planner to a slow planner. So we use this with a couple of different applications. This is the video you saw earlier, which I won't replay because you saw it earlier, that Alan showed, of applying fast track to guarantee that the vehicle will stay within a zone around that line, those series of lines that were connecting the points that Jesse had mapped out using the AR/VR scenario. What we actually have been spending quite a bit of time on in the past 2 years is working on how you might use this to this idea of fast track to avoid people. So to safely maintain a buffer zone with people. And so I'm going to spend just about, well, I guess I have about 5 minutes. So I'll spend about 5 minutes. Oh, I have 15. Oh, nice. Okay. Well, I won't take all 15 because everybody wants the coffee break. But I'm going to talk about how we applied this to moving around people. So, okay, people are more complicated than obstacles in general. Well, they're definitely more complicated than static obstacles, which is all we've really talked about so far. In that they move in ways, and we don't have good dynamic physical models of people describing how they move. So one part of this problem was, how do we come up with representative models describing the motion or even the actions of people so that we can safely plan around them? And so this is, it's actually not okay, so what did we do? We built on some work that has been developed in the mathematical psychology literature. On the left here, I've got these references by Luce and Baker. So Luce is the early reference in 1959. But kind of the robotic planning community adopted this work. And so you see this whole kind of 2016, 2017, these papers, and actually earlier, 2008, so Zibart and all. The people in robotics have taken this work and applied it in kind of the same context that we want to use. But we're going to use it for safe planning, which is sort of different than what's been doing before, different than what's been done before. And the idea is this: if you have a scenario, kind of structured scenarios where people are moving in environments that have goals associated to what the people are doing, so goal-directed motion of people, then one possible way to represent their motion is using a Boltzmann distribution for how they're going to, or the action that they're going to take, where that Boltzmann distribution, so this is the same physics-based Boltzmann distribution with temperature models, that Boltzmann distribution is representing the likelihood of that person acting in such a way such that their goals will be achieved. So let me explain that more concretely. Suppose we have a person that has a goal, and that, let's just say there's one goal now. That goal is moving towards the door, so that there's a door, and the goal is represented by theta. Okay, theta means that's the goal, moving towards the door. The person has a number of actions that they can take, but at the point that they are, the most rational action is the one that that moves the person in a straight line towards the door. So that blue action, so U represents the action of the human. The kind of pink line represents the most rational set of things that the person could be doing in the next few time steps. And then the Boltzmann distribution itself represents a spread around that. So pink represents regions of high probability of where the person will be. Blue represents regions of lower probability. And the Boltzmann distribution is basically saying that the probability of a given human action, which depends on the state, the goals, and a parameter beta, which is a scalar in this Boltzmann distribution, is an exponential distribution. The actions that move the person in the direction of the goal are exponentially more likely than the other actions. That's what that Boltzmann distribution is saying. And the parameter beta is like the inverse temperature parameter in the classical Boltzmann distribution, and it can be used to represent the spread of the distribution or the peakiness of the most likely actions. All right, so for example, if we follow this scenario, person moving towards the goal, pink is the most likely, beta represents the spread. We can think about, as that person is moving, if that person starts to do things which are less rational towards the goal, such as they've forgotten their keys and they turn around and go back, but we didn't model keys as one of the goals. As the person turns, it looks like they're becoming very irrational towards moving towards their goal, and the distribution spreads out. So that parameter beta, as we look at that parameter, we can update that parameter based on what the person is doing in real time. And that's kind of nice because beta is a single parameter, and so just doing a scalar update, this is just a Bayesian update on beta, depending on what the person is doing, is a very fast operation. So if the person's moving towards their goal, we can update beta so it looks like that person's being very rational. If they turn around and go get their keys, we don't know that they're going to get their keys if we haven't modeled it ahead of time, so they become more irrational, and that probability distribution spreads out. All right, so we use that. That becomes our basically representation of what people are doing in an environment. And we use that to represent zones that we want to avoid. As robots flying around, we as the robot want to avoid not only the person, but where we predict the person's going to be in the next few time steps based on this Boltzmann distribution. Okay, so this is just one of the examples here.
We introduce our inferred model confidence algorithm for the same scenario.
So that's Sylvia. And Sylvia is trying to move towards the door of our lab. And there's a quadrotor flying that's trying to plan its path around Sylvia. Okay, so that just shows a kind of
Replaying the
preview of what's going
video,
on.
we can see that
But let's
as
look
the
at
human moves
sort
around
of
the coffee,
top-down view.
the inferred model
So
confidence
Sylvia's
algorithm
moving,
becomes
and there's all this
sufficiently
stuff
uncertain about her
emanating out
future
of
trajectory
Sylvia.
and plans a safe course
That
around her.
stuff emanating, that's actually the next few steps in the Boltzmann distribution. So let's play that again. Sylvia has a goal, and we've modeled the goal as the door of the lab.
We introduce our inferred model confidence
But
algorithm
actually
for the
there's a
same
coffee
scenario.
spill in the middle of the room. And so if Sylvia took a straight line towards the door, she'd step right in the coffee spill. But the robot doesn't know about the coffee spill. So as she starts to avoid the coffee spill, that probability, we update
Replaying
that
the video,
parameter beta.
we can see that as
and
the
you'll see
human
it
moves
here.
around the coffee, the inferred model confidence algorithm becomes sufficiently uncertain about her future trajectory and plans a safe course around her.
Irrational Sylvia. It says, okay, she's becoming irrational. She's not moving in a straight line. Let's spread out her distribution and plan the path. Okay, so this is not safe anymore. This is probabilistically safe because we're taking those fast-track tubes and we're avoiding intersection with some thresholded representation of that probability distribution. And the cool thing is that so we're just doing that with each person now. So now we have two people. There's Sylvia and Jaime. Both Sylvia and Jaime have been working on this Picari project. And they both have goals. They both want to, as you know, it's a small lab space, but Jaime wants to move to one side of the room, Sylvia wants to move to the door. They're both walking through the room. Now there's two quadrotors, which are planning paths to their goals. They're going to have to intersect where Sylvia and Jaime are going to be, so they're going to have to plan paths around them. And we're using an individual Boltzmann distribution for each of Sylvia and Jaime. But there's going to be some interaction, right? There's interaction between people when they cross paths. Sometimes they stop and start talking to each other. Sometimes they just step away to avoid each other. We're not modeling that. But what you'll see in this example is that as the people move, as they start to move away from each other, they're moving away from their straight line paths to their goals. So the robot that's updating this the robots are updating this beta parameter. They model that movement, that avoidance, as being irrational towards the goals. Their distributions spread out naturally, and that creates a bigger avoid zone. And it kind of indirectly captures this interaction between people. So that's our first cut at modeling this. So now we're showing the distributions around Jaime and Sylvia. Jaime's kind of dancing, so he's being a little irrational for the model anyway. You can see that even when even when they're not interacting, Jaime's spread is bigger than Sylvia's because they're looking and going, why is he walking in that? Why is he not moving in a fast line according to a straight line according to the velocities that we set? So, and then the vehicles are planning paths. They know about each other. They know about these distributions around Jaime and Sylvia, and they're using a priority-based multiple vehicle planning scheme using Fast Track that I didn't talk about the priority-based scheme, but we've also developed that as part of our work. Okay, so I think that's a good place to conclude. I'm just going to go to I'm going to skip a little bit here because we don't have time and go to the conclusions. The focus in our group has been on safety-based control, reachability-based controller, and a lot of what we've been doing in recent years has focused on how to make that computation available in real time using different online methods as well as offline pre-computation that I talked about here in Fast Track. And then also how to incorporate learned information on the fly. And we talked about one of those this morning, which is this modeling human motion using a Boltzmann distribution and updating a single parameter of that Boltzmann distribution based on sensed information of what the people are doing. I didn't mention this, but you could probably see in the video that both Jaime and Sylvia were wearing caps in the motion capture arena, and they had little sensors on the caps. So we're just using inertial sensing in the space to capture where both the quadrotors as well as the people are. This is something that we are on this project have been, and with Alan and our collaborators, Roel and Randley, we've been talking about how we can just move all the sensing on board the quadrotors and use onboard sensing as much as possible for this. So maybe to say, we've also been on this project spending quite a bit of time looking at small quadrotors, or developing small vehicles, micro robots that could serve as a multitude of sensory platforms for doing this kind of identification. And let me just thank the students. So a lot of this reachable set technology was developed early on with former students. And they've graduated, and I put kind of where they are now in brackets. Current students are bolded, and the students in red are students that have been working particularly on this project and have been funded by this project. So thank you very much.
Thank you very much. So again, we'll just hold off your questions for later in the open forum. So we'll have a short coffee break. We've been listening to a lot for almost 2 hours now. So coffee break is outside. So I would just like to request everyone to go back to this room. Now it's 10:25, maybe 10 minutes, 10:35. Let's resume about 10:35. And there'll be a presentation on the Philippine side of the switch. So outside, and on this room also have coffee break.
The driver is okay. Last time what happened? Okay, it didn't be the driver.
Yeah, I was at the airport and I couldn't find anyone.
Okay.
It was empty.
It was empty. Okay.
Yeah.
You were at the terminal 1?
I just walk out the terminal. I don't know what
Which terminal? It's an old airport.
Yeah.
Yeah, so that must be terminal 1.
Yeah.
Maybe there was a miscommunication between the driver. The driver was there, he was waiting.
Yeah. Well, the EVA landed in whatever the terminal was. Yeah, I walked out, there was no one there. I texted. I texted the
But I
person.
noticed your text was in it's Apple iMessage.
Yeah, it's iMessage. It should be free.
Yeah, but normally here, maybe they will not all have data. So chances are that guy did not receive the message.
Oh, I see.
Sorry for that.
Yeah.
Yeah, that's the reason why there's always the chance that you will not meet, so I gave you option to use Grab.
Because after I pass the customs, it's already midnight.
Yeah.
So usually I don't call people after midnight, and certainly I wouldn't call you guys. So I just text.
Yeah. And I bet you, Christine was waiting actually. He was awake.
Yeah,
She was awake last night.
Yeah.
But anyway, the driver already met you this morning.
Yeah,
right?
yeah.
That's the same driver who lost you last night.
Oh, okay.
Hey, where were you last night? So you took a cab or Grab?
Is the Fine project joint also with UC?
Yeah, this one.
This,
No, it's
like-
Picari. I'm not particularly sure if it's in collaboration. But
it's
this
to
is funded by.
develop the infrastructure.
Yes, this one's to develop infrastructure so we can distribute the video in real time in universities across the country.
Yeah.
Overview.
Mag-questions kaya mo.
smartphones, right? There's really no reason to upgrade your phones if we stay at a phone factory. However, so if we have more bandwidth, naturally those phone companies like telecom, T-Mobile and so on, they need to convince people to use more of their bandwidth. Otherwise, they are building the infrastructure for nobody to use. So when they push for AR, VR, I think that we will really see more applications. That's actually from the business side going on. I think it's a combination of the new display and the chipset hardware that really need big companies to buy in, and then the new delivery method for the network operators to start pushing for AR, VR. Right? So you will see, one day when we see AR, VR devices as accessories of phones in your cellular phone pop-up shops, the day the AR, VR experiences.
Okay, thank you. I think we can now resume while the system is working.
Okay, okay. So we have to finish as quick as possible. Okay, let's start right away. So the next set of speakers is from the AIRSCAN PH. We will present several algorithms that we develop internally. So just to give you a structure of the talk, as you can see here, at the center, our focus is still on 3D reconstruction, but around it, we develop algorithms that will improve the 3D reconstruction. So Daryl is the first speaker, is going to give you an overview of the baseline algorithm that we use, and then he's going to talk about an algorithm he developed, which is efficient view planning. This is really cool because you can see whenever you fly a drone, normally fly it manually, you just go around infrastructure like a building, but that's not really the optimal way to do it. So he's going to show you an optimal way of doing it, and this is a learning-based system. Now, we built a learning-based system, so we need a good data set, and unfortunately, there's no big data set for 3D. So we built our own data set, 3D model. So Joel is going to present that next. And then after that, an integral part of the efficient view planning is depth estimation. Not just a depth estimation, but a fast depth estimation. So I'm going to present my work in that. And then then Rangel is going to talk about surface reconstruction. You will be amazed that the 3D reconstruction is still relying on an old technique in surface reconstruction. So she's proposing a new technique on surface reconstruction. Then we have point cloud sampling. Raymark is going to talk about that. Inverse graphics, Darwin, and then we will also demonstrate some efforts that we're doing in porting. You saw recently, a while ago, the work on fast track. So we're porting the fast track on our drone, and I think basically that's it. Daryl can start.
Good morning, I'm Daryl Peralta, and I'm a student and an RA of Project AIRSCAN. So I will be presenting first our experiments on the 3D reconstruction algorithms, which we perform to scan actual houses and actual buildings. So in our team, we started with a small-scale experiment wherein we chose this structure inside our campus. This is located in our campus near Paris Museum. And maybe most of us recognizes this. And so the process of 3D reconstruction starts with gathering data, gathering images that we put into what we call a structure from motion algorithm. So this algorithm is an algorithm that uses images of an object in order to estimate the camera poses and also the 3D structure. So from this video footage of our drone that we took, we sampled images and use against SFM to generate this 3D output. So as you can see, the algorithm was able to recreate the 3D model of this structure. So after this experiment, we then decided to proceed to a much larger one, an actual building. So here we chose another structure that is inside our campus. This is a building of School of Urban and Regional Planning, which was during that time was being constructed. So you can see the construction materials there, and this is actually a construction site. We chose this because one of the potential applications of AIRSCAN is to monitor construction projects like this. And again, we took video of at different angles of this building, and we used the existing algorithm in computer vision, SFM, to generate the 3D output that we can see here. So in our implementation, we used the state-of-the-art full 3D reconstruction pipeline, which is open source and which is called OpenDroneMap. And one of the goals of our project is to experience firsthand the state-of-the-art current technology in 3D reconstruction, and to experience the limitations and the problems in it, and build on top of this open source state-of-the-art implementation. So with that, I will now be presenting. We will now be presenting our research works that were motivated by the problems we encountered with the current 3D reconstruction technology. So I will now be presenting my research work titled Efficient View Planning via Reinforcement Learning, which was motivated by the problems we encountered during these experiments. So view planning problem roots from the fact that your 3D model, the output of your classical computer vision algorithm like structure from motion or even depth fusion, is largely dependent on your data. So the quality of your 3D model depends on the quality of your images. So if you have good quality of images, you will have good 3D output. But if you have poor quality of images, for example, incomplete, you will have an output like this. Notice on the parts under the roof, you will see some parts that are missing, holes in it. This is caused by the lack of data on those occluded parts. So this is a problem that we notice in the current technology that we have. This is because the current mapping software like Pix4D offers off-the-shelf view planning like circular path only. So it is not automated. Does not have an idea that it needs to go down to those occluded parts. And even if we do view planning, we cannot be sure that when we run structure from motion, our output would be good or it would be complete. Most of the time it would be like this, which is incomplete. And then we go back to the site and then gather more data. Another motivation is that we experience redundancy in data, wherein if we simply put multiple images to our algorithm that uses multiple images, it will only lengthen time. And we are not sure which of those images are really needed, and maybe most of them are redundant. And in doing large-scale reconstruction, we are using drones. Drones have limited flight time, and in doing this experiments and missions, we spend time and resources in mapping this large infrastructure. So with that, we propose an algorithm that we call efficient view planning via reinforcement learning. So this algorithm is motivated by how a human artist draws a subject. So if you're an artist and you want to draw a person, for example, a portrait of a person, you'll first look at the subject. You will first draw the general outline of the face and then look at specific parts, for example, the eyes, then draw that part, then the nose, then draw it. And it's an iterative process until you arrive at a drawing that is that you are satisfied with the quality as you see the subject. So with that, we ask the question, can an AI agent learn to autonomously scan a house in a much human-like manner? So with that, we use reinforcement learning because it's also an iterative process where an agent could possibly discover an optimized path in doing 3D reconstruction. So here, shown here is the block diagram of our method. The state that the policy uses is simply the images or the history of images. So it's the information that the policy uses to decide on which action to take. And the policy is simply a neural network that commands a new viewpoint to maximize the information gain. So the action is simply the change in pose. So this part of the block diagram is simply the drone sees the current image and then decides on where to go to maximize the information gain. And then at the new viewpoint, it will see a new image shown there and a new depth. So we're using a simulator wherein we can capture depth. And in real life, this can be done using depth sensors or using the fast 3D depth estimation that we also developed. And for this case, we are using depth fusion because this is a learning process, so it undergoes training. So we want to easily estimate the output 3D. So by fusing the depth, we get an output point cloud and compare it to the ground truth 3D model. And we use two measures for the reward. First is the surface coverage, which measures the completeness. And another is a penalty per movement, which penalizes the movement of the drone. So in RL, or in reinforcement learning, the agent wants to maximize these rewards. So if this RL agent learns, it will be able to find a path that maximizes the surface coverage and with a minimum number of steps, which is very needed when we are doing mapping of large infrastructure with drones that have limited battery life. So to start, we implemented our baseline. So again, with the commercial software that we use, and like Pix4D and DJI, it only offers an autonomous path, like a circular path. So here we develop our simulation framework using Unreal Engine, and we also created our own data set of houses that we will be presenting later. And here the circular path will only reach a surface coverage of 87%. So 87% complete and with 17 steps. Whereas our method the agent was able to learn a path that was able to reach a higher surface coverage, meaning more complete with a minimum number of steps. You'll notice that the agent was learned to focus on the occluded parts of the building. It also learned the basic to move around, like there, then move forward and focus on the house, then focus on the occluded parts. That's because that's the path that you need in order to complete the 3D model. And in doing so, it was able to minimize the number of steps. And to compare the output of the 3D the output 3D models of these two path planning or view planning, here you will notice on the left is this output of the circular path. You will see that it has plenty of holes, incomplete models, specifically the parts that are under the roof. This is a common problem when you are scanning a house. But on the right side, we were able to create a model which is much more complete. It was able to reconstruct those under the roof and occluded parts. And to summarize, and to further evaluate our method, we also implemented the algorithm in different RL setups. So first, in a discrete action, meaning the change in pose is discrete. So it's, for example, you want to move to the right, you will move 45 degrees to the right. And we vary that azimuth resolution and also the distance levels that is allowed. So the higher the distance levels, the harder it is for the RL agent to learn, because the farther you are, the depth sensor won't be able to reach the house. And in all these cases, we set the terminal coverage to 96%. And in all these cases, we were able to see that our agent was able to minimize the number of steps and the distance traveled. So for the first setup with 2 distance level, 45 degree azimuth resolution, and 3 levels, the distance was from 662.8 to 482, and from 12 steps to 7 steps. And in all these experiments, we were able to minimize the distance and steps. We then proceeded to change the action to continuous space. So the change in pose is now continuous. And the only difference here is that on the second experiment, we decided to start with a farther distance. So again, the farther you start, the harder it is for the agent to learn, because you have to move forward. And in both these cases, our agent was able to cover the house in a much less number of steps or shorter distance, which is very important when we are scanning using drones with limited battery life. And so to finish this presentation, we have implemented a proof of concept that answers the question, can an AI agent learn to autonomously scan a house in an optimized manner? And we have a proof of concept that it can. And right now, we are working to fine-tune the algorithm and to train it on our own data set, which is houses 3K, for training and evaluation. And we are also planning to see if it can transfer the policy to real world. So that's all. Thank you.
Alright. So as Daryl discussed, a large number of data set is needed in order for his system to learn efficient view planning and reinforcement learning. A large number of data set is needed for that. And for the other research for our project. But one of the problems we encountered in this was the lack of data set. Most of the data set that are available are mostly on 2D and point cloud. And if there are 3D data set, they focus on the interior of the houses and not on the whole structure and the totality and forms of the house. That's why we decided on creating our own data set. So now we are presenting Houses 3K. By the way, I am Joel Casimiro, lead artist of Project AIRSCAN. Houses 3K is a collection of 3,000 3D models of different houses with different variation, different structures, and different texture and materials. Initially, our goal is to create a massive data set of large urban infrastructure. But initially, we focus and we narrow our scope on creating data set of houses with variation of size and structures, from one-story houses like a bungalow-type house to four-story buildings. We start on researching for our style vocabulary. We research on the houses forms that are usually used, their structures, their roof types, window and door styles and designs, and even roof and wall textures. And from this style vocabulary, we translate it into a 3D modular assets. Yeah, as seen here, every type of windows and doors that we set on our vocabulary, we translate it into a 3D modular asset that we can mix and match like Lego to design different types and different kinds of houses. So every batch of modular asset, we target to create at least 50 different house models with each. And each house model, we iterate them using 5 different textures. So every house is iterated in 5 different textures to give more variety. Then after that, after we created those house models, we evaluate it using, we ran it on Unreal Engine and using Open Drone Map to validate if the texture and the structure of the houses that we created in 3D is good enough for 3D reconstruction. So as we can see here, the ground truth is the input, the 3D objects that we create, and that their constructed image are on the right side. There are some fail cases on the 3D reconstruction wherein the initial reconstruction image is pretty messed up and not good with not good structure. If that usually happens when the wall and the house structure have less details. So we have to iterate on the textures and the structure of each houses and run it again in the evaluation. In this case, we tweak on the texture of the initial house, and as you can see on the third picture, it produced a better 3D reconstruction. As of now, Houses 3K has 12 batches, 12 modular batches. Each 12 modular batches has 50 FBX and OBJ models, fully textured and can be rendered. And each of the 50 models have 5 different texture maps. Texture with diffuse and normal maps. So it could simulate the creasing and the actual structure and the actual texture of the walls. We could also categorize it by its structure. Currently, we have 605 one-story building, 1,232 two-story houses, 550 three-story houses, and 615 four-story house. Then further work would be adding some more data set on this and making sure that each asset is watertight and the edges and the topology of each mesh is seamless and work well within the need of the training the research requires. Thank you.
Okay, I'm given 5 minutes, so I'll start right away. As you can see, in the efficient view planning, a very important algorithm there is the depth estimation, but it's not really just depth estimation. It has to be very fast. Okay, and as if you're working in the field of robotics, okay, it's not just coming up with an algorithm. As you can see earlier, the talk, we need to come up with an algorithm that's fast, efficient, computationally efficient. It's not power hungry, and with this in mind, we developed this algorithm, which is called fast depth estimation, using dense networks. It was published in ICRA last year, and I just want to point out two codes. Number one is the code of the anonymous reviewer, ICRA, that this algorithm, a fast learning model with few parameters, is really a cool idea. And to move this forward, we should always keep in mind this quote from Rodney Brooks. He's one of famous roboticists in the world. We should keep in mind that we cannot afford to put even the results of machine learning on many of our small robots. Self-driving cars consume about 2,500 watts of power for computation. A human brain only requires 20 watts, but I think it's just 1 watt, so I'm not sure, but that's Rodney Brooks. So moving forward, we need depth estimation. Even humans, we do depth estimation in real time. It's very important because otherwise we will not be able to navigate ourselves and we will hit objects in our environment. So depth estimations has many applications. It's required in autonomous car navigation, in 3D reconstruction, and in the efficient view planning, as you mentioned earlier. This is a very important part of, this is a very important algorithm in the robot motion planning. This work has 3 key contributions. Number one is we were able to come up with a very tiny network, just 290,000 parameters. If you compare this with many state-of-the-art depth estimation, they require many millions of parameters just to implement the same performance. So this is really suitable for drones or mobile robots. And then because of this small set number of parameters, it can perform depth prediction at the very fast rate, even higher than 30 hertz. The accuracy did not actually suffer. It's sometimes even better. Now, just to give you a quick overview of what disparity is, in case you don't have background in computer vision, just imagine you have 2 images, left and right, just your image, and take 1 pixel, for example, the corner of the roof of the car. That pixel on the left image will appear on a different location on the right image. The distance called disparity. That disparity is actually a measure of depth. Okay, the relation between disparity and depth is shown by this equation. And in this equation, as long as you have calibrated the camera, the focal length and stereo camera baseline are actually constant. So that means this equation implies that depth is inversely proportional to disparity. So the bigger the disparity, the closer the object is. Now, this is dense map. The intuition behind the architecture design is very simple. If you take 2 images, if you design a network that can measure the correspondence, that output of correspondence network will become the input to this disparity network, which will then apply a relative disparity on a reference image, in this case, the left image. You can see there on the right, the disparity prediction, we call it disparity map, is very close to the ground truth. Now, if you want to take a closer look at the architecture, this is the architecture. The corresponding network is actually, instead of getting deeper, it's getting wider. And the output of this goes into the disparity network, which is actually a very deep network. So, so the output of the correspondence network is combined with the reference image. In this case, it's a left image. Now, so what's the secret sauce of this architecture? How come it's able to reduce the number of parameters that's so small? The secret sauce is actually we're using a lot of compression, a lot of cooling, a lot of skip connection, and a lot of upsampling. And take note that we're doing here, right? We're working on high resolution images here. So to benchmark this data set, we use synthetic and real data set. The real data set is based on PT 2015. It's actually a famous data set. It's actually derived from that car. It's collected using that car. So they have stereo camera there, and then they have LiDAR on top, and that car will drive around Germany, and the LiDAR provides the ground truth. Training this network is really simple. It's end-to-end. So that means you dump the data set, the training data set, and then you validate it with the test data set. Now, before I show you the performance benchmark, let me define first the metric, which is called endpoint error. The endpoint error is like this. It's very simple. Suppose you have the ground truth on the right, and this is the prediction on the left. Take a pixel, okay? And the measure of difference between the two pixels, the absolute value, is actually the endpoint error. So the endpoint error is computed for the entire image. Now, the performance metric. Take a look at this performance metric. This was published last year. During the time, the state-of-the-art is DisNet. SGM is a classical method of measuring disparity. MCE, CNN Fast is another technique using deep learning. In single driving, Flying Monka, and PT 2015, 3 out of 5 actually were performing better than them. In terms of number of parameters, take a look at the state-of-the-art. It's 38.4 million. That's impossible to use on a drone. Okay. And we're just using 0.29. Because of this, we can operate at much higher speed. And considering we're using a more inferior GPU for this case. So lastly, let me show you a video. The rendering here is this actual speed of rendering and measuring the disparity. So first is the synthetic, and then the last one is the real images. Technique, we're going back to the other algorithms.
Okay, so good morning. I'm Rachel Garoy. I'm also one of the MS students under AIRSCAN. And my topic for today is more about surface reconstruction. So like already mentioned, the main topic of our project is more on 3D reconstruction. And I'm going to be telling you more about the different ways that we can represent these 3D models that we want to create. So first, I want to discuss some of the different forms we have of 3D models. So there are mainly 3 types: point cloud, volumetric, and mesh. So usually we get point clouds directly from our images. So if we have a set of images, the first thing that we can get is a representation of point clouds. So they are easily acquired. However, there are usually gaps in its representation. So there are usually holes, and there's not a lot of continuity in its surface. So we have an alternative, which is the volumetric representation. It gives us a better idea of the actual surface temperature of the object. However, it's represented in discrete space, so that limits the amount of information it can give us. So this leads us to the third representation, which is a mesh, which is more continuous in its representation of the surface. So in general, a mesh provides more information because it gives more surface details in a way that the surface is continuous. And furthermore, texture can easily be more incorporated into mesh representations, which is why my work mainly focuses on these kinds of representations. So from a point cloud that we usually get from a set of RGB images, my work aims to translate this point cloud representation to a mesh representation. So we call this surface reconstruction. So I'll be talking more about how we go about this problem. There are already existing approaches that try to solve this. So there are mainly three types, where the first type is mainly concerned with the classical approaches, and the last two types are on learning approaches. So the first type, given a set of points, these methods usually interpolate between these points to form the final surface. So most problems arise from these methods when we have sparse point clouds. If we have very few data points representing an object, we usually get a lot of inconsistencies with the representation. So that's why the first method can't work. So we have the other two methods, which are learning-based. The second method usually deals with default mesh structures, for example, a sphere. And these methods use a latent representation of a point cloud to deform this sphere, so they get the final object representation. So they, starting with the default sphere, they use the latent code to deform it until they get the final object structure that they want. And then the third method creates the final mesh, not just by deforming an initial mesh. They also predict the actual interconnection. So the second method usually deals with just moving the vertex positions, having a fixed interconnection, while the third method predicts both the interconnections and the vertex locations. But the limitation with both methods is that they both have fixed interconnections, so their outputs are fixed to a certain number of vertices, so it makes it less flexible in the representation they have of the objects. And what we aim to do with our work is to make this representation more flexible. So for example, if we want more detailed mesh, we would want higher number of vertices. And if we want to represent a simpler object, maybe a fewer number of vertices would do. So in order to address this, what we will do is we try to make it a generative approach. So we try to generate interconnections one by one, in contrast to other methods that usually start with a fully connected graph and then remove edges one by one. What we want is to progressively grow the mesh and just add vertices, or edges rather, as we move on and as we see it fit. So it's more dynamic mesh construction, and it won't be restricted to a specific number of vertices. So in order to do this generative approach, we utilize a recurrent neural network. So our work is mostly inspired by the graph RNN architecture, so based on this figure. So what they try to do is, this work focuses mostly on generating graphs. So they generate graphs composed of nodes and edges. So they sequentially introduce nodes to the graph, and as they add nodes, they generate the interconnections. So they add nodes one by one, and as nodes are added, they generate the edges that interconnect these nodes. So we can relate our work with this architecture by associating nodes with vertices and the edges of the graph to the actual edges of the mesh structure. So the main pipeline goes something like this. So say we have a delayed sequence of interconnections or adjacency matrix, which represents the edges of the mesh. And then we feed it to a recurrent neural network that would predict the graph state, and then feed it to another recurrent neural network that would predict the interconnections to give us the final mesh structure. So to give you a better idea, let's have an example. So say we have these sets of points. This represents the point cloud that we initially have. So what our network will do is it will order the points, so say from 1 to 8. And this will be the order at which the vertices will be inputted or fed to the network. And as these vertices are sequentially fed to the network, the interconnections would sequentially be predicted as well. So say we feed the first vertex first, and then we have the second vertex. Now the network will try to predict which interconnections this new vertex will make to the existing vertices in the mesh. So it will say that, okay, I'm going to be connected with vertex 1. And then as I introduce more vertices, the network will again try to predict the interconnections it has with the already existing vertices in the mesh. And it will iteratively do this sequentially for all the vertices until it completes all the interconnections and create the final structure. So from a set of points, using the recurrent nature of the neural network, we're given this more complete picture of what the real surface actually looks like from just a set of points. So the main advantage of this is it's generative. So we started from 0 edges or interconnections, and then we progressively grew it depending on the need of the representation. So unlike the other methods that usually start with a fully connected graph and then reduce it one. So these are some of our preliminary results. So you can see on the left-hand figure the target interconnections, and on the right-hand figure are predicted interconnections. So this used the recurrent neural network architecture, and as you can see, it is somehow already able to get the target interconnections. Okay, so as a whole, so my work mostly focuses on the translation of point cloud representations to mesh representations. So it makes use of these sets of points that represent a 3D object. So it's still an ongoing work. We're still doing a lot of validation and experimentation on this, but I've already shown you some initial results in the previous slides.
Good morning, everyone. So I am Lauren Bautista and part of AIRSCAN solution. And on behalf of Dr. Chesa and the rest of the team, I represent our work, Dignet, Inverse Graphics Network First Insights in this. Now, this work is mainly concerned with inverse graphics, or the process of inferring possible scene structure just given a observation. So that's how we humans actually understand the world. Now, the main motivation for this is that computers with this level of understanding of the 3D world would be very useful in various applications, such as self-driving cars, or the new planning that our variables we're working on. So as humans, we could probably infer a 3D scene structure like this. So in this work, we refer to this as the inverse graphics process. So our work is motivated by this, and to this end, we present the BigNet, vision as inverse graphics network. So this is an end-to-end neural net which jointly performs segmentation, recovery of fluid parts, estimation of camera viewpoints, and finally reconstruction of the BBC. Now, in the following slides, I'll be working through the process on how we arrive at the full 3D construction given just a single image. So we start with the 128 by 128 RGBA image containing 2 overlapping objects randomly sampled from 5 classes. Now, this scene is static in the sense that the scale is off and the angles are off, as you can see here. But this serves our purpose well, so we use it. By the way, we generated this dataset because when we started working on it, there wasn't an available dataset with all the annotations we need. So given this image, we use a capsule encoder to arrive at the vector representation of each of the objects. So at this point, we will have 2 capsules, and then we decode each image using an image decoder. So we arrive at 2 separate 128 RGBA images containing just 1 object per image. At the same time, we also decode the poses from the capsules. So we obtain 2 sets of camera viewpoints, 1 for each object. Then we use a 3D reconstruction algorithm called pixel-to-mesh to arrive at separate 3D reconstructions for each object. Then, using the pose that we predicted earlier, we can now create the full scene 3D reconstruction. Now we evaluated, by the way, the main difference of BigNet to other models is that existing models could only operate on the visible pixels, whereas our network could infer the most possible shape and texture of the fluid part, like you see here. The pose parameters that we predict are the distance, elevation, and azimuth. This basically tells you where the camera is relative to the object. Now, we evaluated our work on the areas, the segmentation, performance, and painting, and accuracy of pose estimation. Since there are no work that does all of these jointly, we compared our work on the state-of-the-art models on each area. So first, for the segmentation performance, we compared against GitLab version 3 and PSDN. And we can see here that the mean IOE, which is a measure of how well 2 sets overlap, BigNet has the highest score. So the maximum score you get here is 100, which means that 2 sets perfectly overlap. The top figure shows qualitative results. So you can see here that the BigNet output is the one closest to the ground truth. Now for the input inequality, we use two metrics, the mean squared error and structural dissimilarity. The mean squared error is mainly concerned with the pixel values. So you can see that it's more concerned about the texture of the images. On the other hand, the structural dissimilarity is more concerned about the shape. So in terms of the MSE, the top model in this case is context encoder, although the performance of our model isn't far behind. But in terms of the DSSIM, we can see that BigNet outperforms the other models. Now for the post-estimation accuracy, we compared it against variants of BGG network and the baseline CNN. So for the first 4 entries here, these are the percent errors when you are estimating the pose one object at a time. You can see here that BigNet is the best performing model in this case. But when we try to predict the poses of 2 objects simultaneously, the performance degrades a bit. So here are some qualitative results. The images on the left-hand side are the input images, and the right-hand side shows the full scene 3D construction. So in summary, we presented BigNet, an end-to-end trainable inverse graphics network that is able to jointly segment, predict pose parameters, recover occluded parts, and finally reconstruct a 3D scene. The performance in all 3 areas are comparable, if not exceeding the state of the art. That's all. Thank you. Thank you for listening.
Good morning. I am Raymar. I am also a MS student here under Project AIRSCAN. So my topic is point cloud of something. So first, what are point clouds? So point clouds are simply an array or list of coordinates and or features. So you can see that the data is actually just an array of numbers, but this doesn't really mean much to you. But if you try to project it in 3D space, this list actually corresponds to a point cloud of a chair. So point clouds, 3D scanning technology has been improving with the rise of technologies like Kinect, LiDAR, but the problem with these sensors are that often their output is sparse or incomplete, which may lead to poor 3D reconstruction quality, especially on detailed sections of the object. So to further illustrate, this is a 3D reconstruction of the chair that I've shown a while ago, but with the varying number of points as input. So you can see that when we use 512 points, the 3D model is very incomplete. While if we use more points, 8,192 for example, you can actually generate a very good model. Okay, so point clouds are being used more and more in deep learning, mainly because they are simple and uses less memory compared to other representations like voxels. So, but the problem is typical convolutional deep learning networks require structured inputs like those in 3D voxels and images in order to perform learning. So, since point clouds do not have a regular structure, early works on this usually convert them first to voxels before learning. But this introduces a quantization errors and also increases the memory usage. So how do we go about this? So there are actually main challenges on point clouds are actually first, it is permutation invariant, which means that if you try to shuffle the list, it actually still represents the same shape. And it also has no structure, as I said a while ago. So, for example, if we have a point cloud here, wherein the number represents the order in the list, and the color represents the feature vector, and we have another point cloud here, it's the same shape, it has the same shape, but with a different order. So if we try to force this into a more regular structure, it would look like something like this, while the other point cloud would look like this. So, and if you try to use a convolution on these 2 point clouds, this will actually result into different results. Although they are, even though they are actually the same shape. So how do we go about this? So there have been several approaches to learning on point clouds. So here are just some of the works that have been using point clouds for learning. So first is PointNet and PointNet++, which uses one-by-one convolutions and max pooling in order to solve the permutation problem. While the PointNet++ introduced a hierarchical downsampling in order to learn at multiple scales. Some other papers have been also published, like Dynamic Graph CNN and Point CNN, which uses wherein they introduce a new type of convolution in order to learn on point clouds. So actually, in my current approach, I am using the PointNet++. Okay, so to introduce the upsampling problem, so first, given an unordered set of d-dimensional points, we want to get a generate a new point set with more points that lies on the underlying surface. So the idea is actually very similar to 2D super resolution, but this deals with 3D points rather than pixels. This is very challenging when the input is very sparse and when your output needs to have complex geometric structures. So the current approach that I am using is actually borrowed from CycleGAN, wherein CycleGAN is actually used to create a mapping between 2 domains. So, for example, here they made a network that can convert photos of zebras into photos of horse, and the other way around. So to expand on this, we can think of CycleGAN as having 2 parts, which is the GAN part and the cycle part. So the GAN part is mainly, the idea is when you have an input of a horse and you input it to a mapping function f, we hope to create a fake image of a zebra. Then we input this to a zebra discriminator, wherein this discriminator will identify whether the input image is a fake or real. And aside from that, we also input an image of a real zebra, so that the network would learn the difference between the real zebra and the fake zebra, so that it would eventually the mapping function f will be able to learn how to transform an image of a horse to an image of a zebra. And they also do this on the other way around, wherein they create a mapping function g in order to transform zebras into horses. So it uses the same concept wherein they input a fake image of a horse and a real image of a horse in order to learn how to create the mapping between the 2 domains. So, and then the cycle part is basically we're using both functions f and g in order to transform an image of a horse to an image of a zebra, then back to a horse. And the idea is the input should be the same as the final image after inputting it to the 2 mapping functions f and g. So why am I talking about this? So the idea is that I want to create a mapping function from a domain of sparse point clouds and to a domain of dense point clouds. So here we have a sparse point cloud as input to an upsampling mapping function, which learns how to upsample points. And this upsampled point cloud is inputted to the downsampling network in order to create the downsampled point cloud. And we use this so that the downsampled point cloud would be the same as the input sparse point cloud. And similarly, we also input the sample point cloud to a discriminator so that the network would learn the distribution of dense point clouds and sparse point clouds. So this is also done in the reverse cycle, wherein we downsample again first, then upsample again. So here is the preliminary results that I have made. So there's an input point cloud of a house, which consists of 5,000 points, and the output is a point cloud of the same house with 20,000 points. Currently, it is still a work in progress, and since the output is still not very good, and it still has noise in it, and it's not very obvious here, but there are actually still points generated inside of the house, which is not ideal because we only want points to be on the surface of the object in order to create the surface constructor. That's all.
Morning everyone. I'm Izan Andoni. I'm a student as well as an RA working under AIRSCAN. So this morning I'll be talking about the steps we're taking so far in order to start implementing a safety algorithm for metrics. To start off, basically the main motivation behind this is that given that the goal of AIRSCAN is to scan around buildings for construction purposes, of course there's the need for a safety algorithm to be implemented in order to prevent collisions and possible accidents. So with this, our partner institution, the University of California, Berkeley, already provided a good algorithm for safety for UAVs in general, which they call the fast track, as Professor commented a while ago. So I'll be discussing the theories behind it and instead we directly jump onto its implementation. So shown here is the diagram for the online computation of fast track, wherein you have your tracking states, which is eventually your drone, which will send in its current state in the form of position and velocity, and this along with your planner, which will give in the next virtual state of your drone. The controller will complete for the needed control signals, such as the roll, pitch, yaw rate, and thrusts, and sends it back to the drone for execution. So eventually, the safety algorithm that we're trying to implement is the fast track done by Berkeley. So they already provided the code for this on their GitHub account, but the examples and the dynamics was modeled after Crazy Fly, and so the porting cannot be done straightforwardly. And given differences in our setup, we also actually have to fine-tune some of the blocks, such as in getting the position for the drone, as well as doing some experiments to look at the sensing capabilities of our sensors. So here is the overview as to the implementation of both teams, the drones and the sensors used, as well as the assumed dynamics and where the computation will take place. So in our case, we'll be using the onboard GPU of the Matrice 100. So basically, in porting fast track, even port fast track, one of the challenge that we saw was we encountered was in resolving the inherent inaccuracies of the sensors that we used. So for example, in localization, the Berkeley side used OptiTrack, if I'm not mistaken, which is a motion capture sensor able to resolve up to a millimeter level of accuracy. And given the limited resources we actually have, we have to do some compensation for it. So initially, what we used was that we used the DJI GPS with hovering accuracies of 0.5 meter vertical and 2.5 meter horizontal in order to get the position states. So what basically does is that it gets the longitude and latitude of the drone and then converts it to corresponding XYZs with respect to the initial home point recorded by the drone. Now, the problem with this is that this heavily dependent on the GPS signal, wherein based on our initial test, our drone actually had trouble of getting. So if we leave it as it is, it would lead to potential inaccuracies in the position we're getting and could lead to possible errors. So to illustrate my point, shown here is the position graph taken from the GPS data shown on the left, and on the right is the ground truth position. So this was conducted inside our drone cage outside, just outside this building, wherein the recording started on the red dot there when the drone was already in flight and the good GPS signal was available. So this was manually controlled using RC, wherein we did as per our mission, let it land before taking out of the cage. Now, as you can see here, when good GPS signal is available, it was able to give good results and relatively accurate results. However, when the GPS signal was lost, as represented there at the bottom, there was an erroneous signal generated, wherein there was a sudden shift in the X direction when in fact there shouldn't be any. This could be a result to the drone resetting its position onto its initially recorded home point. So this kind of scenarios is something that we do not want. It was a good thing that it happened. In this case, it happened when the drone has already landed, but it would be problematic when it happened while the drone is on its flight. So which would lead to potential crashes and or the drone getting lost. So obviously, workaround is needed here, wherein we have to remove the dependency of the drone onto the GPS signal. And one of the things we look at is actually the guidance system. The guidance is first and foremost an obstacle sensing device, but it also throws in position data in the form of XYZs with respect to a certain reference point. So given the exact same scenario earlier, wherein we actually, when we did the test, we recorded the position data from both GPS and guidance, and the data from the guidance actually showed better results and less noisy results. And then here is one of the flight tests we conducted, wherein on the right, we allow the drone to run autonomously, to do a spare mission autonomously. And shown here, there are two problems. One is that it depends on GPS signal, so it actually has to fly a certain altitude in order to get that. And the second is the inherent inaccuracies of the GPS, wherein the trajectory was slightly angled because of those inaccuracies, even though when it was coded, we usually fly straight. So if that drone flew any lower, and especially without a good obstacle sensing device, that drone would no doubt crash onto that building, that main building we have there, which is something that we do not want. So, but with, for example, adding in guidance, so even at a lower altitude with low signal, the drone should still be able to position itself. So, in addition to the position problem, one of the things we also look at is explore the sensing capabilities of the sensors we have. So in this case, DJI guidance. The guidance uses ultrasonic sensors and camera to sense its immediate surroundings. So it has a sensor range of about 0.2 meters to 20 meters. So in this case, we actually coded a simple program wherein the drone will utilize one of the sensors of the guidance, particularly the one in front. And then when it senses an obstacle along its path, it will try to go over it. However, unfortunately, we weren't able to conduct a real-life test run yet due to the So to summarize, basically, again, our goal is to implement a safety control, or in this case, that algorithm is the fast track done by Berkeley. This is still a work in progress, and more still needs to be done. So what we've done so far is that we conducted tests in order to explore the capabilities of our drone, as well as fine-tune some of our sensors to get more accurate data, which is really essential, such that when the fast track is ported, a more accurate data will be given and the computations will be correct.
Sir Ron, so that concludes the presentation from the Philippine side. So maybe closing remarks.
Okay, open forum.
Open forum.
Maybe 5 minutes.
Okay, so we'll entertain some questions. Maybe 5 minutes, yes. From Alan first and Claire.
Claire.
Yeah.
Should I use the microphone?
Yeah, sure.
Yeah, thank you for those really nice presentations. I wrote down a couple of questions as we were going through. One was related to, Rangel is working on surface reconstruction with mesh representation, and then Raymark talked about the point cloud upsampling. So I was interested in the connections between the two projects, because I think, Raymark, you gave a nice justification for why to do point cloud upsampling. And I think Rangel gave a very nice justification as to, suppose you have a point cloud and you want to basically do a surface reconstruction. So when you're looking at the respective projects, is there a sense of what the trade-offs are? Like, is it, you want to get a certain number of points so that you get a better surface, but could you push the limits and perhaps have fewer points and use a better algorithm to get a better surface? Or where does the line lie between how many points you need to be able to get a good surface and sort of pushing that so you need fewer points? It seems like a really nice interface between the two projects.
That's my question.
Exactly the same.
Yeah. What's next? It's going to be a superset of you guys doing, or?
Well, mostly my work really deals with very few points. If you have few points, it's really hard to do the reconstruction directly using the existing methods. That's mainly where my work concentrates on, dealing with these very few points. What framework aims to, I think, really just upsample, so have lots of points so that when we use the existing algorithms, they would work seamlessly so that the actual surface is reconstructed for the final mesh still is has high fidelity with respect to the original structure. But in terms of the clear boundary between,
I don't think there is a clear boundary.
Yeah.
I think it's always going to be different for different problems and things. It was interesting to see both of your presentations looking at different sides of the problem.
it's more of like approaching the problem in different ways or in a different direction. So we directly from a sparse representation to a complete mesh structure. As for Raymark, it's mostly from a sparse point cloud to more denser point cloud representation.
As she had said, the goal of my topic was to upsample it so that we can use the existing classical methods to create the 3D models. But there, I can see the connection wherein for her topic, it would be very hard to create the mesh from sparse point clouds. So we can actually look into that. That maybe we can, instead of solely using sparse point cloud to create the mesh, maybe we can interconnect our networks so that it would be easier for her network to create the mesh.
Thank you.
I have a follow-up question. So, in addition to the general, where's the interfaces also, I want to also ask about, I know when we do speed reconstruction, I'm playing also into AR, VR. I think the nightmare is when you have holes. Yeah, right? So no matter it is low quality or good quality, is fine, right? So I'm just playing Minecraft, I'm playing Pokemon Go, that's fine. But when you are in virtual space, low resolution is one thing, but having hole is a totally different thing because that actually is not visually pleasing. So in that case, if you have holes, in your case, if you have sparse mesh, you have sparse point cloud, you definitely are going to have holes, but you are trying to use mesh to fill those, right?
Yes, exactly.
But for you, when you want to upsample the point cloud, also there's certain aspect of filling the holes, right? So in terms of just particularly applying to filling the holes, which have you used your different approaches to try to see filling the holes, and what are your experience to address that problem?
Hole filling.
Mostly with the mesh reconstruction, it's more easily solved with the hole filling because the goal of the mesh representation is to have a more continuous surface. So with the method that we're trying to develop, we really look into the hole filling as part of the problem. So with what we're doing, I think we're overcoming that hole as with the point cloud.
Actually, for mine, I'm actually still having problems on that. Since ideally you would add more points to the parts that you know that would have more details. So ideally, by adding points there, you would be able to address the whole problem. But as of now, I'm actually still having that problem.
Thank you. Robert, actually, my second question is not actually a question.
I think that actually I'm going to put out a proposal. I think we should really continue. Yeah, so you guys are really having a tour force presentation. But I think that in particular for another project, you guys are building a map of different buildings.
Yes.
I know that I didn't mention to you, and because that was not part of the initial program, so we're actually building a one-to-one map of Berkeley campus.
Okay, I see.
So it's the entire Berkeley. So what we want is to turn Berkeley into an AR/VR test bed. So I think that's certainly, without, communicating, I think we are doing something, very, very similar. So I think we should talk.
Yeah, sure. No problem with that.
In terms of land area, which one's bigger?
I think UP is bigger.
Yeah. More land area.
Well, I'm not sure. Is the mountain part of UC Berkeley?
The mountain?
Yeah, you have a mountain beside UP.
Oh, so that's actually...
the Lawrence Livermore.
That's outside the boundary.
So
you cannot do anything. You cannot take pictures from that part.
Okay.
Yeah. But
so UP is bigger, I think, without the mountain.
So maybe we can entertain one or two more questions from the audience. Richard from Samsung R&D Philippines.
I have a question for Claire. Okay, because Samsung is actually very interested with robotics, especially the sensor robot. One of the interesting topic that you have discussed is about the obstacle avoidance. So you had mentioned about the model for humans. So I'm just wondering if, for example, in an environment with pets, is that a model also for pets?
Well, we have so the questions about like cats and dogs and other pets. We haven't tried that, but we have. There's a project that's going on at Berkeley in our department, done out of one of the computer vision groups on predicting motion from images. So predicting, you see, so this is a network that's trained on lots and lots of images and videos on the web. And they're predicting what happened from an image, what happened right before and what happened right after. And they're doing it with humans, but what they did previously was with pets. So we've been talking with them about more detailed models of, because this the model that we looked at is very, it's goal directed, and I mean it's useful in some context, but it's not useful if you're going to do interaction. So it's not just avoiding people, but interacting with people, and so we could think about more detailed models and also what goes on with pets.
If Samsung is willing to fund, be willing to take on using it. Okay, so any questions from our interesting audience? I think, yeah, Clear will still be here in the afternoon, but on a different research agenda on electric grid markets, I think. But Alan will have to fly out this evening, so if you have questions, you could probably, maybe you don't have questions right now, but you have questions later in the future. Please feel free to send questions, mainly to Roel. Also AIRSCAN and also to my email. So we'll just curate those questions. Maybe some of your questions are one and the same, and then we'll just forward them to either Claire or to Alan. Yes, question.
Hi, I'm Kirsten, an undergraduate student from Tripoli. I want to ask Sir Alan Young about what he mentioned about not having about there not being any standards with AR/VR yet. So is that part of your ongoing research? Are you trying to define standards for AR/VR? And if you are, what considerations are you taking into account?
Right. So I think that's a huge question, and I don't think that at this point we are actually not planning to design any standard. What we actually want, and we also know that when you build interfaces, it has to be task specific. which means that whether you are trying to do 3D reconstruction or you want to do drone delivery, which means that number one is the way you talk about standards. You want to make sure that that standard is for passive users or for collaborators or for supervisors. That's actually very, very important. Right now, we are actually seeking, as we moving forward, a sense of optimality. So we want to know that for performing certain tasks, in addition to just making sure that the implementation is better than manual control, if just among different options in virtual reality or augmented, what is the optimal way of doing certain tasks? So it's very task specific. Currently, we have two tasks. Number one is the search and rescue, and the second one is warehouse delivery. In fact, the search and rescue is actually part of our effort for building the Berkeley one-to-one map. So the reason is because we envision that building the 3D map is not going to be, as I mentioned, that you put a sensor and then you do a sweep and then you put another one. You can do it one time, but we have to have a volume solution to that. I think the difference in engineering is that you cannot do a one-of-the-time system. So that's called a trick, right? So, but if you have a solution that works all the time, that work in Berkeley and also in Manila, then it is this is a solution. That's just a theory. As they say, right? So if one thing works one time, it's a trick. If you want 2, 3 times, it's an algorithm. Right? It's a theory. So what we want is to do that. And the second one is that we want the model that we build to have a millimeter accuracy. So I think that is important for AR and VR. I think that's also different from autonomous driving. For autonomous driving, you can have 1 meter error. As long as you know that you are on this street, driving this direction, that is good enough for cars. But for AR, VR, if you just have a 1 centimeter error, I'm projecting in here, you're going to see me jittering like this. But in order for me to really like a Neo that stand here and then without any jittering, so that also was the question that Roel was asking, right? You are in the AR, VR space, currently you see all this imperfection. That actually was created by the sensor and the data not having the enough accuracy. So we're actually trying to use that and hopefully can use drone to automate it. So we're actually designing the interface and also the underlying algorithm to try to just to expand a bit.
Thank you very much. No more questions? Closing remarks or do we? Well, we'll take over.
Yeah. I'm the only one standing between lunch and you. So we'll close this one. First and foremost, we're fortunate to have Alan and Claire to be here. And that's we're going to give them
as an appreciation of your flying all the way here from
this UP maroon shirt, or because we have a very good basketball team. We win every 2 decades. Okay, this is for Alan.
Thank you so much.
Thank you.
Picture.
Thank you. Thank you. Oh, there.
Very much. Thank you for being here. Thank you. So lunch will be served outside room next to adjacent room, and also upstairs. So we are officially, for those who need the certificate of participation for this seminar, just contact Christine at AIRSCAN at EEE.ph, just outside the registration desk. So with that, we are formally closing the workshop. So thank you very much, everyone, for attending.